All right, everybody, we're going to go ahead and get started. First off, can someone just give me a nod that they can hear me and see me and all that good stuff? Okay, awesome. Thank you, guys. Okay, so welcome back. It's good to see everybody again. Hopefully, you've had a good few weeks and been getting your feet wet with nuclear medicine and with your clinical sites and with all your fun classes and homework. So, um, glad to be back with you. I wanted to cover just a couple of things real quick to get started today. One of them is just I was looking at the test and I wanted to give you guys kind of an idea of how that went. So you guys did pretty good. It looked like a pretty standard bell curve kind of test. Um, we did have a couple people get 100%, so the bell went all the way up to 100 on one end, and then the lower end was somewhere around 74, 73%. And so that's pretty good. All of that would be pretty close to passing for board, so that's awesome. You guys did a good job. Again, I would, and the vast majority of you were in the like 90s to 95%. So that's good. Um, I would encourage you again, please do your test corrections. Like we mentioned before, I don't require them because it's hard for me to put that into a grading system and make it equal for all of you guys. But it is part of the learning process. So if you haven't had a chance to do those, please do those. And again, there were a few of you that have not taken the test yet. As I mentioned before, I don't usually do due dates on those things because I know your lives are hectic and crazy with clinicals and work and everything you're doing. So, but please try to keep up. If you haven't taken that test, try to do it quickly so that you can now move on to the next section here and get that done. So that would be good. Try to keep up. Again, if any of you are having issues keeping up or something going on in your life that is crazy, just contact me. I'm pretty chill and we can work with each other to make this happen for you. Okay. Okay. I'm today is a lot of information. We'll definitely take the full 2 hours. As I always do, I will tell you that we're supposed to go from 9 to 11, and so at 11 o'clock, if I'm not done, I'll continue the lecture, but I will not be offended if you need to leave. I know you all have plans and schedules and things like that. So my typical practice is if we're not done, I'll just finish the lecture. It'll all be recorded and then posted on the Canvas so you can get anything that you didn't get before. Okay. Okay. Let me think here. I think that's about it. I'm going to go ahead and get us started. Let me get my slides up. Unless there's any like burning questions, if it's specific to maybe something just for your grade or your test or something, I would prefer to do that one-on-one because we need to keep all the time. But is there any general questions that I can answer right now? Okay, perfect. All right, give me just a minute to rearrange my screens and get the slides pulled up, and we're just going to dive into this because we have quite a bit to cover. All right, can you guys see my screen good? Okay, Dallin's giving me awesome. Got a thumbs up from Jessica. Okay, cool. All right, so just as a reminder, guys, with these lectures, I tend to get yappy and talk. So please interrupt me for questions. I'm totally good with that. You just pop your microphone on and totally interrupt me. I don't care. If you have any questions, just pop right in, and we'll get started. Okay, so today is awesome because Today, we're actually going to look at the stuff you guys use on a daily basis, right? Your number one thing you use in nuclear medicine is your gamma camera. So we're finally getting into how does this stuff work? How do we produce an image? So this is a fun lecture. Again, it's in depth and there's a lot here. So I'll encourage you to go over these slides again. Another kind of maybe reminder too is that my slides, what I try to do with my lectures, because there's a lot of information, is distill down everything into understandable basic principles, things you need to know. But it's not meant to supplement for the text and for studying. And on your boards and even in my test, you can get questions that are maybe not things I covered in detail or specific. So I would always please encourage you to read the chapters in the text, to go over them. They'll give you nuances that I may not give you, and I may give you nuances that the text might not give you. So please look into those. But having said that, I'm really excited to get into gamma camera today. So this will be fun. Okay. So the name of the game for us in nuclear medicine is radiation detection. If you think of anything that we use in nuclear medicine, basically what we're trying to do is detect radiation, whether that be our gamma camera, which we're going to talk about today, or whether that be survey meters or anything else we use in nuclear medicine, we're really trying to detect radiation. And kind of the three tasks that we really are doing is, of course, we're trying to produce diagnostic imaging. We're also we do therapeutic dosage delivery, and we have to detect radiation from that, to give those things appropriately. And then, of course, to calibrate our equipment, we use radiation detection. And so those are kind of the three main areas that we use in nuclear medicine. I've got a chart right here that kind of shows all of the different things we use. You'll notice you've got like your dose calibrators, GM survey meters, surgical probe, ionization chambers, thyroid probe, well counter. We've got our gamma camera, which I've got highlighted we'll use today, PET CT, compact gamma cameras, dosimeters. All of these things are radiation detection devices, right? So in our next lecture, we're mostly going to cover gas-filled detectors. This one we're going to cover the gamma camera. And we'll probably cover a little bit of the well counter and the thyroid probe in the next one as well. And then dosimeters, we kind of hit when we do our quality assurance class, which is actually in the summer. But again, all of these are just detection of radiation. A lot of them work with some similar principles and some different principles. But we'll cover gamma camera today. All right. So when you think of what we're trying to do, the purpose of an instrument in nuclear medicine is to detect and record gamma events. And you have to think what we're trying to do is we're trying to detect a gamma event in space. In other words, where did it happen? When did it happen? Is also important for us. We do things like flows and things like that. What was the energy of that radiation, right? So was it TEC? Was it I-131? Can we determine what we're looking at? And then the other thing that we want to know is how much of it is there, right? All of these things are necessary in order for us to be able to get our images or do anything that we do in nuclear medicine. So I want to bring up a couple of principles that we've sort of covered in our last lecture, but kind of bring them to your mind so that you can think, as we're going through some of these principles, you can think through things correctly. And one of the things is the photoelectric effect. Now, we talked about this last time, and we talked about it in reference to our patient, right? And you guys that are X-ray techs, you know about this. The photoelectric effect is where we have an incoming photon, and in the case of our patient, an incoming photon that strikes an atom, and we eject a K-shell, right? And we get characteristic radiation, and that ups the patient dose, right? So you're used to thinking of it in terms of patient and thinking, okay, photoelectric is bad, right? Because it just is dosed to my patient and it kicks out some scatter characteristic radiation, right? So we need to shift your brain just a little bit, because we want the photoelectric effect in nuclear medicine. Now, we don't necessarily want it for our patient, but we do want it for our camera. And let me ask you a question to help us kind of start to understand why. So this incoming photon, and in our case, it would be a gamma. Who can tell me what happens to this incoming photon?
It's completely absorbed.
What was that?
It's completely absorbed.
Exactly. Who was that? That was Bree, right?
Yeah.
Okay, awesome, Bree. Thanks for being brave. Exactly. It's completely absorbed. Now, why would that be important in nuclear medicine? Anybody have an idea? Why are we so interested in that gamma photon being absorbed completely? Any guesses?
Is it because it doesn't travel anywhere else? It stays right where it was supposed to go.
Tori. Yes, I think you're on the right path. Thank you for being brave. Anybody else? You're on the right path. That's not the total answer, but I think you're thinking correctly.
Would it be to see what the body does after it's absorbed?
Okay. Remember on that answer, I'm going to say remember that we're talking at this point. We're not talking about our patient. So that's what I'm trying to shift you, right? Normally, you're used to thinking about the photoelectric happening in your patient, but we're gonna talk about how the photoelectric effect is important outside of the patient and with our camera system. Go ahead. Somebody was gonna say something.
Is it because like our cameras are like catcher's mitts, so when it's emitted, it's absorbing it to make the picture?
Okay, now we're getting along the right path. Okay, think about this. And to not spend too much time here, I'll just go ahead and answer. But all of you, you're thinking in the right direction. So the incoming photon, it was mentioned by the first person, it is fully absorbed, right? And everything with nuclear medicine is dependent on measuring energy, how much energy is there, and also what type of energy is there. And so if we don't get complete absorption of that photon, it's ineffective for us to be able to measure it. So one of the principles that's important here is if we can completely absorb a photon, then we can accurately measure it, whether that be measuring to make a pixel on our screen or measuring it to make look at how much radiation is present. But we like the photoelectric effect when it comes to our equipment, because if we can fully absorb the energy, then we can accurately measure it, okay? So think of that principle as we go forward and talk about the gamma camera. We need to be able to absorb that energy and accurately measure it. Because we've got to get from energy all the way to a picture on our screen, and we've got to keep that accurate and measurable the whole way through, okay? So one other principle that's important, we looked at this last time. Remember that gamma rays are a sinusoidal wave. They're just energy, right? On one end of the spectrum, you got radio, you've got visible light here. We don't think of light as it doesn't have mass. It's not a thing. It's a photon. But remember, it's very, very high energy, and it's so tightly bound, or so tight when it gets to this gamma ray end that it almost does act like it has mass. It almost acts like a thing. So we're going to talk about photons today and what they're doing through this process. But keep in mind, it's almost like tight packets of energy. And then the other thing to really kind of think about and remember is that, I put it right here, how do photons travel? Or in other words, how does radiation travel? Well, it travels in 360 degrees. And really that's 360 degrees cubed, right? So on this right here, I've got 360 degrees, but that's in all directions, right? It's going 360 degrees. So we have to think about that when we start trying to capture a picture. Every time you get a photon or an event within the body where there's radiation, it's putting out radiation everywhere in all directions, right? So we have to think about that as we start to capture things and radiation, okay? So those are a couple principles to keep in mind. What we're going to do next is I'm going to go over some properties that have to do with all radiation detectors. And it's going to seem a little bit convoluted. So let me get through these next 3 or 4 slides kind of explaining general principles. And then as we talk about the gamma camera, I'll reference back those principles and where they fit in. These principles will also somewhat apply when we talk about gas field detectors next time and some of the other equipment that we use in nuke med, okay? So properties of radiation detector, we really have 2 main headings that we think about. There's detector efficiency, or sometimes called sensitivity. You'll hear both of those used. They mean the same thing. And then there's also system resolution. Okay, those are the kind of the 2 main things, sensitivity and resolution. Within sensitivity, you've got geometric sensitivity, intrinsic sensitivity, and photopeak sensitivity. And we'll talk about all 3 of those. And then in system resolution, you have energy resolution, temporal resolution, and spatial resolution. So let's talk first about the efficiency or the sensitivity. So when we think about sensitivity in a camera, all we're saying is that think about your patient, right? They're giving off radiation, and they're giving off a certain amount of radiation in 360 degrees. So your camera, when we talk about how sensitive the camera is, it's how of all of the events that are occurring or are available, how many of them can we actually detect and use to turn into an image? Okay, that's how sensitive or efficient your camera is of the events coming off, how many of them can we grab, capture, and use? That's sensitivity. Okay, I mentioned the components of geometric, intrinsic, and photo peak. So geometric is the idea of kind of where your camera's positioned, right? So the radiation has to hit the detector in order to be detected, right? So that's your kind of geometric, and that can change depending on camera size and shape and where things are sitting, things like that. Intrinsic is how well can that energy be deposited into the camera through some sort of interaction, right? So when we do get when we do get events striking the camera, how well can we then get those and turn them into something we can use? And then photo peak efficiency is when I see those events happening, can my camera detect what type of radiation that is, what type of event that is? In other words, can I make a determination between I'm seeing tech and I'm seeing I-131 or some other thing, right? Can I make a delineation between those things? That's photo peak efficiency. So I kind of mentioned, again, this is kind of said most of this just now, but we'll briefly go over it again. But so this is geometric, right? So under efficiency, or again, geometric, one of the things that really makes a difference is source to distance. In other words, your patient, how close are you getting the camera or whatever device you're using? The closer you get that, the more efficient you're going to be at gathering all of it. And if you think about that, it makes sense, because if radiation spreads 360, the farther away it gets, the more spread out it is. And the closer you get, the less spread out it is. So you're able to grab more of it, right? Pretty simple to understand. And then the other one is detector configuration, which I mentioned. So that's like size, shape, type. Is it surrounding it to like a well counter, right? A well counter completely surrounds the dose that you put down inside. So a well counter would be really, really geometrically efficient, whereas a camera is only one head. A PET scanner is 360 degrees, right? So that's geometric efficiency. Intrinsic efficiency is can we get something absorbed in the detector, right? And this is going to depend on the type of radiation, the energy of the photon. We're going to talk about different detector type, collimator types that you use today, and those matter on how well we can get intrinsic efficiency, how well can we absorb what's hitting the camera. A lot of this will depend on the thickness of the detector, the density of the detector, also the energy of the photon. We have this right here called attenuation coefficient. And in other words, how much is blocked by different parts of the camera or by the body. Again, both of these are determinants of the photoelectric effect, right? If we have a high Z number and a high attenuation, that means it's going to absorb the photons that contact it, right? So that's what we think of when we think of intrinsic. How well can it absorb that energy that it sees? And then again, a photo peak, can we discriminate energy of events within a certain energy window? Meaning, can we detect what we're looking at? Okay, what are we seeing? Okay, so that was all the sensitivity stuff. Okay, now we'll quickly go through kind of the more detailed concepts of resolution. So energy resolution, we're so used to thinking of more like spatial resolution when we think of when we think of things like X-ray or things that you've done before, right? We think of resolution in terms of the ability to see between two shades of gray, things like that. So energy resolution, you just have to change your brain a little bit. Energy resolution is just, can I discriminate between what I'm looking for? In other words, if I'm looking for tech, I'm looking for 140 keV versus any scatter or other events that might happen that would be lesser energy, right? can my camera determine the difference between those two and what it's trying to look at? Okay. I wrote some things here, but that's kind of the gist. In an ideal detector, all electronic pulses would result from complete absorption of a specific photon, right? Which is also the importance of having the photoelectric effect, is if I can fully absorb it and I see how much energy is there, then my camera can say, well, I'm positive that I have TEC, or I'm positive I'm seeing iodine or something else, right? So energy resolution. Can the camera resolve that energy? We're going to talk about a principle today called full width half max. And that's how you measure the spread of resolution, or if you're getting good energy resolution. So we'll talk about that. Temporal resolution. This is the conversion of signal energy, in other words, going from a photon to an electronic impulse, which is eventually what we need to be able to put a pixel on our screen. So can we convert, and can we start with knowing what we have, what type of radiation we have, and how much energy it is, and then keeping that process all the way through till we get to an electronic pulse. In other words, when we get this electronic pulse, does it in energy represent what that photon was, right? So that's temporal resolution. Or if we have bad temporal resolution, we lose some of the energy and we can't tell what we've got over here when we're an electronic pulse. But if we have good temporal resolution, when we have that photon and then we get to electronic energy, it looks exactly like it should. It registers as 140 keV for TEC. Okay, and then we'll talk about a principle called dead time. That will apply more when we talk about our gas field detectors. It's still a concept in cameras, but I'm not going to cover that really much. I don't think you'll be tested on that. When it comes to dead time, you will probably be tested when it comes to your gas field detector. So understanding this is important. But dead time essentially is that when we talk about temporal resolution, going from a photon to a electronic pulse, there is a time at which that takes. And when we talk about this time, we're talking about nanoseconds. It happens very, very, very quickly, right? But there's a time from going from here to here, there's a time that takes place, okay? And there's a couple of things that can happen. They call that dead time. There's a couple of things that can happen in that time. One is that you can have what's called non-parallelizable, okay? So what that means is that when your camera sees a photon and it starts to send it through this process of becoming an electronic pulse, it's going to see it, and it means it's going to complete that system. And if it sees another pulse, it will go back, it will complete its original thing and then go back and see the other one, right? So it's every time it sees a pulse, it's able to put the process through. That's called non-parallelizable. It's just gonna, every pulse it sees, it sends through the process. Parallelizable is a system that needs an uninterrupted processing time to go from the signal or the photon to the electronic impulse. And so what that means is if the camera sees something and it starts sending it through that process, if it sees something again, this original process is erased and it goes back to the first one. It wants to complete the whole process before it starts over again. And what will happen is if you get too much radiation going on and it's trying and trying and trying, it never is able to complete the process and it pretty much shuts down the system. That's what we call parallelizable. When we talk about a GM survey meter, we're going to talk about a parallelizable system. So just know the difference that non-parallelizable, it sees each event and can make the process happen. Parallelizable, it needs that full time, that dead time to complete a process, and it will mess it up if it keeps seeing it, okay? A little bit confusing. Again, like I said, as we talk about things, it will make more sense, especially next time. And then spatial resolution. This is the system's ability to demonstrate detail, okay? And what this means, you're used to resolution in X-ray, again, meaning the difference between where you see dark and light, right, on film, things like that. That's kind of the resolution. Here, that resolution is, can our camera represent something spatially where it occurred? In other words, if I have, let's say I'm doing a heart, and so my biggest radioactive organ is the heart, and my camera is above me, can that accurately be represented in the right placement on the camera? And you'll get this in more detail as we go along, but can we accurately represent where radiation is occurring? or does it slightly move, right? And we're going to talk about what makes our camera have better resolution. In other words, representing something where it actually occurred, okay? And then when you think about spatial resolution, the principle for nuclear medicine, of course, instead of looking at grayscales, what our camera needs to be able to do is represent the difference between where an event happened and where there's no event happening. And that's where we get that resolution, okay? And we'll also talk about the principle of full width half max in spatial resolution, which is how we do a quality assurance and determine we have good resolution. Okay, I know that was weird and convoluted, and go back and listen to that again and look at those principles. Those principles are covered in your textbook as well. Now we're going to get into talking about how the gamma camera works, and I will try to pull those principles in as we go, okay? So the way that I've found over the years is the easiest way to teach this is we're just going to follow the path of the gamma ray. Okay, so the gamma ray, you put that in your patient, you put your nuclide in the patient, you've got gamma rays coming off. So we're going to start going from the patient, the first thing we hit in the camera, and traveling all the way through to where we get our picture. Okay, so we're just going to follow the path. Oh, and then on here, you may hear either textbooks or possible test questions. I think they're getting away from this now, but you'll hear something called an anger camera. An anger camera is just a gamma camera. They were originally called anger cameras because the scientist who kind of came up with the principle of the gamma camera, his last name was Anger. So if you hear anger camera, that's what they're talking about. Don't stress about that too much, but just put that in your file in the back of your head. I will never refer to it as an anger camera. It's just gamma cameras, okay? All right, so the first thing that we hit in a gamma camera is the collimators. Now, again, all of you that have been in X-ray, which is I think a majority of you, I need you to turn off your X-ray brain because collimators in nuke med have some similarities, but they're quite different, okay? So we need to readjust what a collimator is in your head. And collimators are, I would say, it's important in X-ray in a couple of different ways, but it's not one of the main foundations of producing your image. You know, it definitely affects patient exposure and things like that. But in this one, it's one of the main things that helps produce our image. And so it's different and important we understand how it works. So I have these listed as kind of two principles of what collimators do. I probably should rearrange these two principles because I would say the more important of these two is number 2, reject unwanted photons. So the two things collimators do is define the field of view and then reject unwanted photons, okay? So you'll notice this first bullet point, collimators are the image forming aperture of the gamma camera, so super important. Collimators are made, you can see this is actually a piece of a collimator, right? So your collimator goes across your entire camera head, but you'll notice that what you have is you've got what we call bore holes, which are the little holes, and they're inside a septa. So the septa is basically the material in between the holes, right? So usually these are made from lead or tungsten, something with a very high Z number, high density. And so you've got the bore holes and then the lead walls called septa, okay? Again, what this is gonna do is think about selective absorption. This is going to determine which gamma events are able to get to the camera and which ones are held out, okay? So again, rejecting unwanted photons. Now, when we say that, and I'll have you look at this principle right here. This is interesting. As I start to explain what these do, think back on this, that less than 0.1% of gamma rays actually make it to the detector as events that we can use. That means that of all that stuff coming off, we get rid of most of it in order to form our picture. And here's why, okay? So what does this do? Why? So down here, I've got a representation of a body. And you'll notice right here, we've got the bore holes with the lead septa in between. Again, we're kind of looking at it from a side view, so it doesn't quite look like the picture over here. But the idea is we've got the bore holes in the septa. Now, what I want you to notice is first, let's look at D. Now, I want you to remember when I started this, I said radiation goes in 360. So we're just going to say we're noticing one photon. And this one photon, I want you to notice it's basically traveling parallel to those boreholes, right? And what you notice is that because it's traveling parallel, it goes up, it goes through a borehole and is able to strike the crystal. And we'll talk about the crystal in a minute. It's able to strike the crystal, okay? You'll also notice that because it travels perpendicular and goes straight up, that this radiation spot within the patient is demonstrated exactly in the spatial place that it is on the camera head, okay? It's represented exactly where it should be. Now, let's go over to B. What happens with B, now remember, on B, we're going to look at this photon that's traveling at kind of a 45-degree angle. But keep in mind, there's also photons from B location, which also traveled parallel and made it to the head, right? Made it to the crystal, just like on D. But now we're going to look at what happens in an angled photon. So a photon that comes at an angle, what it's going to happen is it's going to come up and, oh, look what happened. One of those septa, it struck the septa, and because they're high Z number, it's going to absorb that photon, right? And so that photon does not make it to the image. Now, think about this for a second. I said when we looked at D, it went parallel, right? It went straight up, and it was able to give us, this is what's going to form a pixel on our screen. So it was able to put an event right exactly where it actually happened over the patient. If we didn't have this septa here and we let B go, then the event that actually happened here on the left side of the patient would look like it would strike up here, maybe where this A1 struck. It would strike up here, and it would look as though on our picture that event happened somewhere in the middle of the patient, when in actuality it happened over on B, right? So this is how collimators are starting to form the image. We only want parallel photons that are parallel to the septa, okay? Parallel to the septa. Why? Because they can get through and be represented exactly where they happened in time, or excuse me, in space, right? In space on the camera head, okay? So that is what the purpose of the collimators are doing. That's why we say reject unwanted photons, but let the wanted photons through. And what are the wanted ones? They're the ones that travel parallel, okay? They travel parallel. Not parallel to the camera, parallel to the septa and the boreholes. They travel parallel, okay? Again, I'll point this out now that you kind of see that we only get 0.1% of gamma rays that are coming off your patient. So our system already is pretty inefficient, but we have to do it this way, because otherwise, if you didn't have collimators on and you just had your patient get under there, it would be like shining a flashlight. You get just light, or in this case, gamma rays in all directions. It would just flood the camera, and you would get nothing that was a picture, right? There would be no resolution. There would be no image formed. It would just be a bunch of whiteness on your screen, okay? So that's the idea of purpose behind collimators, okay? Here's another view that maybe is a little bit more accurate, right? So all of these points down here are representing an event or radiation within the body of your patient, the gamma rays. And so you'll notice that from that one event, there's gamma rays coming off all over the place. And you'll notice that most of them are being blocked because they're angled, they're being blocked by the septa, okay? And then the ones that are represented where they should be, which is parallel, are getting let through. Now, one thing I want to point out with this particular graphic is, let's look at this one right in the middle here. You'll notice that it is super parallel, like it travels right up the center of that borehole and is represented exactly where it happens in the image. What you will notice then, I want you to come over maybe to this one on the far left side. You'll notice that it originates down here, and it actually is traveling at a slight angle, but that angle is not steep enough that it doesn't make it through the borehole. It actually does make it through the borehole, okay? This is what determines some of the resolution on a gamma camera. And a gamma camera, about the best it can do on a static image is about 3 to 4 millimeters of resolution. And that's usually about the size of the borehole. And that's why, is because you'll get photons that are coming parallel, but maybe slightly off. So they're going to be represented as slightly in the wrong place in your image. And
is that why some of the images are fuzzy? Like you don't get crisp lines?
Yes, Ashley, that's exactly right. That's why when you look at a CT scan, it's like, wow, that thing is crisp. And you look at a nuke med, it's a little fuzzy. I've had doctors that call nuclear medicine, they switch the N and the U and say it's unclear medicine, right? Because we can only get a certain resolution in a gamma camera. And this is why. This is how it works. And you can imagine, you might say to yourself, well, why don't we just make those boreholes a lot smaller? Well, they're already about 3 millimeters. So the smaller you go, what you're going to do is every time you get smaller, you're rejecting more photons. And what do we need? We need photons. Our image is literally formed by the amount of photons we get. That's why when you stick a bone scan under there and you count that to a certain amount of counts, right? Well, because we need that many counts to form an image. I don't know if any of you have ever seen, I think I was in like Disneyland, or I can't remember, but there was an artist and he was doing people's portraits, but instead of drawing lines, he was only doing dots. So he would make people's pictures by doing dots, right? And if there was only a few dots, like when he first started, you couldn't tell what the heck he was drawing. But after he got thousands of dots on there, it started to form an image. Well, we work really the same way, right? And so our resolution, we can't get those boreholes so small that we don't get enough coming through, right? And so we have to make this trade-off. And we're going to talk about in the next few slides, or actually I think the next few slides, but we're going to talk about this trade-off between how much we let through and how much we cut off, and what that does with our efficiency, which is, remember, the number of photons we get, and our resolution, which is representing them where they should be represented. So thanks for interrupting me, Ashley. That was awesome. Okay. So let's talk about that. Okay. What affects collimator sensitivity? Now, to remind you of sensitivity, it's what's available coming off, like we referenced in those general principles. What's available coming off? How much of that can I gather of what's coming off the patient, right? What's available versus what we get. That's what I put in parentheses down here, okay? And the way that's actually defined in the book is it says number of counts received per minute per microcurie of activity. Don't get too held up on that. Just know that sensitivity is being able to detect those events and how many you're detecting. So here's what affects sensitivity: borehole diameter, septal thickness, and borehole length. Okay. So we kind of started to reference in the last slide, why would borehole diameter make a difference? Well, if you've got a small diameter, less is going to get through. If you open up that borehole diameter, you're going to get a lot more through, right? Because a lot more is able to get through, even some of the ones that are angled. So bigger borehole is more sensitive. Smaller borehole is less sensitive.
Energy, low resolution, low energy, high resolution, different collimators come in?
Yes. Yep, you're exactly right. And we're going to get a trade-off between resolution and sensitivities. You're exactly right. That's exactly where we're headed. Good job. So the other one is septal thickness. Okay, and we're going to talk about why you would have a thicker septum in a minute. But if you can imagine, you've only got a certain amount of space on your camera head. So if you have holes of a certain size, but you make the septa bigger, then there's going to be less holes to go for that space, right? So you're going to have less that's able to get through. So again, septal thickness is going to make a difference in how much gets through. And then the other thing is borehole length. And there's some stuff I'll show you on that, some graphics. But the longer, if we go back here, if we make this borehole, this one that was slightly angled that got through, that's all the way on the left, if we made this borehole a lot longer, eventually this photon at that slight angle is going to strike the septa and be stopped. Okay, so if you lengthen out your borehole, it's going to have less coming through, so less sensitive. Okay, so a shorter borehole is going to allow more of those angled photons to come through. Longer borehole will cut some of those off. Okay, so that's kind of your sensitivity on the collimator. Now let's just like Ashley was talking about a minute ago. Now, what does that do to resolution? So let's talk about what the boreholes and things do for resolution. Okay, so remember, perpendicular photons, perfectly perpendicular photons give the best resolution because they're represented in the correct place. Okay. Non-perpendicular photons are slightly moved, like we talked about, from where they're originated. So borehole length, okay? If you get a longer borehole, just like we mentioned on this one here, If this is coming in at an angle, which means something at an angle is slightly off in its resolution. In other words, it's not going to be represented perfectly. So if you're slightly off and you get a really long borehole, eventually it's going to hit that septa, right? So borehole length is going to affect that. It's only going to let perfectly perpendicular through. So when we increase borehole length, we increase resolution. Borehole diameter. How does borehole diameter affect? Well, if we make the boreholes bigger, then you're going to have photons coming through that are able to make a bigger angle within that borehole. If you shrink that borehole down, then slightly angled ones are going to go away. So with our borehole, when we have smaller boreholes, we increase resolution, and when we have larger boreholes, we decrease resolution. And then the other thing is distance, our distance from the camera. And I'll show you a graphic on that one in a minute. We'll come back to that. But just to say it out loud, distance, the farther that you are, that your patient is from the camera, your resolution is going to go down. And when we bring them close, the resolution is going to go up. And I'll give you a graphic on that one's easier to understand. Okay. So let's look at this graphically on all of these. Okay. So effects of borehole length. So this is a good graphic on borehole length. So I've tried to represent the event happening within the body in the same spot. And these are exactly the same spread. And what you'll notice, and I've put the collimators at approximately the same spot. So with this shorter bore length, right? What you're seeing is angled photons getting through. Okay, you're seeing a lot of angled photons get through. And then you're seeing over here when we've lengthened out that borehole, again, some of those photons that are angled are still getting through, but a lot less of them because of the angle, right? They hit that. Now, let me ask you a question. I want you to think of what we said about sensitivity and what we said about resolution, okay? The two things. In this scenario right here, when I go from, actually, let's see, let me ask it this way. So this picture on the left, is the resolution, which one of these has higher resolution is the first question I'd ask. Is the left higher or the right higher on its resolution?
Right.
Okay, the right, exactly. Right's higher, right? Because of those photons get through. Which one has more sensitivity?
The left.
The left. Okay, so what you're seeing here is that sensitivity and resolution have an inverse proportionality. They're inverse relationship. Okay, this is a battle we have to make in nuclear medicine between getting good resolution and getting enough counts. And it's a battle we have to come to a happy center place. There's not a perfection on either side. The more efficiency that we let through, our resolution comes down. The more we do things to make those boreholes longer and so forth, the resolution, improve that resolution, then that efficiency goes down and we don't gather as many counts for our picture. So this is a game we have to play with our gamma cameras. Okay, so this next slide kind of represents that collimator resolution versus sensitivity. So we can increase sensitivity by increasing the bore, the hole size, and decreasing bore length. So those two things will increase sensitivity, but those two things will also decrease resolution. As the opposite, resolution may be increased by a smaller borehole size and increasing the length, right? But again, those two things are going to be the opposite for sensitivity, okay? So try to get these in your head. When you think through it from a perspective of how the photons are traveling, think of it in that way, then it's easy to kind of get in your head. But just know that they're inverse, that we battle between the two, and that this is also the reason why in Nuke Med we don't have perfect resolution like in other imaging modalities.
I have a question.
Yep, shoot.
I think I'm confusing myself. So with collimator resolution, it's better if the photons are perpendicular.
Correct.
And then collimator sensitivity, it's better if they're parallel.
No, so it's not going to be the traveling. So the sensitivity is just how many photons did you gather of what's coming off the patient. How many did you get? So this is a good representation of that. So the sensitivity, if we could capture all of these photons, then our camera would be super sensitive. but we can't, right? We have to block some of them, otherwise we don't get an image. And so this represents the sensitivity that we have. It's only going to let things through that are parallel to some degree. Now they might be slightly tilted one way or the other, okay? But it's going to let those things that are parallel through. If it was perpendicular, it'd be traveling this way, it would definitely not get through. So the idea is this, just that the more we are able to gather, the higher sensitivity it is. And the more perfectly parallel, the greater the resolution. And so again, we have to, the septa length and size changes, and the borehole bigness, how big the borehole is, lets less through or more through or less through. Did that help? I don't know if I answered it for sure.
Yes, thank you.
Okay, all right. Okay, any other questions on resolution versus sensitivity? Okay, so go ahead, somebody had it.
Yeah, Jesse asked a question in the chat.
Oh, thank you for monitoring chat. Tell me what it is.
I was
Is there a
curious
way to
if
use
there's
a-
like a way to thanks, Ashley. No, you're good. Instead of just having a flat crystal that's only going to pick up the perpendicular ones, is there any sort of textured ones that are able to get like a degree and tell that it's coming in at a 15-degree angle or whatever
Yeah,
and
great.
make better pictures?
Great question. So we're going to reference that a little bit when we talk about PET. So PET is made up of crystals that surround the entire board of the camera. So there's some applicableness to there. We're going to talk about different types of collimators coming up, and that principle is used in some of those different types of collimators. I haven't necessarily seen a curved crystal, but there are some collimators that change their shape and configuration, and we'll do that next. So good question. Yeah, it's a good idea. I like you. I mean, it's awesome thinking that way. So you should invent one. Make yourself rich. All right, so the last thing on here is just, I talked about distance, and so this is kind of showing you what happens with distance. So I tried to represent the camera being the same here, and then the source of radiation is close or further away. And so what you'll notice on here is I tried to do a similar spread. When your patient is far away from your head, you're seeing that a lot of these are getting through, but a lot of them are quite angled, right? So your resolution is highly affected when you increase that distance. It takes your resolution down, and that's the main thing I want you to think about when you think of distance. Is you'll notice over here, you ended up with that perfectly parallel photon coming through. Okay, now this is going to seem almost opposite. I don't sometimes even like to mention it because it can tweak your brain when you're trying to just learn this. But you might think from this that, oh, well, if I have a greater distance, I get more sensitivity. The reason that's not the case is because, again, remember, radiation spreads in the 360, but these, say I had two photons that were going out, the further distance away, these photons get farther and farther apart. But if I come down really close to these photons, they're actually right together. So when your camera head is close, you're getting better sensitivity than if the camera is way far away, because half of your radiation isn't even striking the camera, even having a chance, whether the septa stop it or not, even having a chance, right? So you might think from looking at this graphic in a simple way, well, if I'm farther away, then I catch more sensitivity. It's actually not the case. Don't dwell on that too much with your brain. Just put that in there as knowing that distance is good for sensitivity. Getting close is good for sensitivity and for resolution. Okay, it helps both. This is why I'm sure you've seen in your clinicals so far that you'll have some techs that get the camera really close and some techs that don't worry about it and they leave it far away. Get your camera as close as you can. Now, I understand there's patients who are claustrophobic, or there's issues, right? You got to do what you can do to get your patient through the scan, but you will get better resolution and a better picture if you get your patient close, and this is why. Okay, so we want to get close. Be a good tech, get as close as you can, take care of your patient, but you're going to get a better image the closer you get to your source. And this graphic just kind of shows specifically on resolution and sensitivity. what happens on the different types of collimators. And we're going to go over those different types of collimators next. But it shows the sensitivity and the resolution and what happens with them. So just remember that distance affects resolution, affects sensitivity. Shorter distances is better. Okay, so now we're going to get into those the types of collimators, what we have and why. Okay, before we get to kind of the configuration, which is more of what maybe Jesse was referencing in principle, we need to talk about their energy classification. So there's 3 energy types. So when you're at your clinicals, and not every gamma camera you come across is going to have all 3 of these. It kind of depends on what your facility does. But there's 3 kind of energy levels or types of energy classifications. There's high energy, medium energy, and low energy collimators. And I have listed here the energy ranges that you typically use in KEV for what you would have. So like, and I listed an example here, high energy is usually somewhere in the neighborhood of 300 to 400 KEV range. And that would be like I-131, or medium energy, which is 200 to 300 keV. So like maybe gallium or indium, which you may not use much of those anymore either. But those are examples. And then low energy, of course, would be like 60 to 140. So this is like your tech. Most of the time, you're going to have the low energy collimators on there because most of the time you're imaging tech, right? So what makes the difference? How are they different inside for these different energy levels? And really the main difference in these collimators is septal thickness. Okay, they're differentiated by septal thickness. A higher energy collimator are going to have thicker septa. And if you think about that, well, why would my septa need to be thick? And it's because you have really high energy photons coming in, right? And what does a septa have to do? It has to be able to stop unwanted or non-parallel photons, right? So if we need to do that and we have something with super high energy and our septa are really thin, well, it might blow right through the septa. When that happens, if you were to take I-131 and then put them under a low energy, like a low energy collimator, you might get a little bit of blow through, or you might get some low energy scatter. One of the things that's called is septal penetration or septal crosstalk. That is a term they use in your book. That could be something I could see thrown on a test, like what is septal penetration or what is crosstalk? And that's when you don't have thick enough septa and you're getting scatter and you're getting blow through those septas. And that does nothing but degrade your image, right? So higher energy collimators have a thicker septa to block higher energy photons. Lower energies have a thinner septa. Again, with thicker septa, fewer photons pass through. So what that means is that the higher energy collimators are a little less sensitive. So typically you have to image a little longer to get enough counts, right? Because if you look at the difference between this low energy collimator and this high energy collimator, you notice like these boreholes end up being quite a bit bigger than these boreholes down here, right? So it does affect the sensitivity of the collimator. So that's what you look at when you look in clinicals and you're looking at what's the difference between these energy collimators. That's the difference. You'll also notice as you're moving them around, depending on what kind of camera you have, some of them have like carts that you move it on. You'll notice that those high energy ones are heavier, but because they have more lead or tungsten in them, right? They're a little heavier collimator. Okay, so that's your energy classifications. Now we'll talk about the geometry with the configuration types. There are manufacturers that have some specific ones that aren't exactly this, but these are kind of the 4 basic and what you'll probably be tested on. So we're going to cover parallel hole, diverging hole, pinhole, and converging hole collimators. So this first one is diverging. Now, this is often used when you have a small camera head or a small crystal, and you still want to be able to image larger objects, okay? So there are, most of the cameras that are probably in your departments have probably like a 40 centimeter field of view, kind of a standard size, or they could even be bigger than that. In some small clinics where they're trying to use Nucomed, I've seen some in like some small heart clinics, things like that. To save on costs, they have a smaller camera head. And what happens is they they angle those septa out. And what that allows, you can imagine if I had a camera head, so you see the thickness on my body here. If I had a camera head that was, say, this big and everything's traveling parallel, the only thing you're going to see is what's right over that camera, and you're going to not be able to detect a wider body part, right? But if I take those septa and I angle them out, then photons coming maybe from my shoulder, but they're traveling at an angle, are going to be able to come and hit the camera, right? So everything kind of coming into that center place is going to hit that. What it does is it take that on your image, it takes a big object and it minimizes that object. So it allows a bigger object to be imaged by a smaller detector. This is going to reduce sensitivity a little bit because a lot of those parallel and other photons are going to hit. But again, anything traveling parallel to those septa, which you notice they fan out. So not every septa is exactly the same. They slightly fan out. So anything that comes in at those angles is going to be accepted. And what that's going to do is create a small image version of whatever you're trying to view. Again, my guess is that you probably won't see these much in practice. Does anybody know, do any of your sites have a small camera head or maybe a cardiology department that's using a really small head? Possibly. That's usually where I've seen them. You probably won't see them a lot. I guess no. Yeah, I didn't expect anything. But that's what a diverging does. Just think, makes a big object come in smaller, and you've got that fan pattern going out, reduces sensitivity. Okay, so that's diverging. Converging collimator is pretty much the exact opposite. So now the septa, instead of being fanned out, they're all kind of pointed in or coming in towards the center. What this does is it allows a small object to be then magnified bigger, okay? This actually increases sensitivity, and the reason why is because you'll notice that this type of fan pattern, and Jesse, this is where I would kind of say you had kind of an idea come in your mind. You'll notice this fan pattern exactly matches what you would expect from radiation, right? Radiation goes in 360, so it's fanning out in that manner. So this is matching that, and so you get your parallel, the septa are kind of in the natural parallel to the way radiation or light travels, okay? And what that does is it takes a smaller object and makes it larger. Some of these are a fan like this, where they're running parallel along one length of the collimator, but then they're fanned in, or you can have other ones where it's almost like a pyramid. So every side of the collimator is fanned in to kind of a central point. So we have camera heads on our SPECT camera in cardiology where I work that has a converging collimator coming in every direction from every side to a central point. And the idea of that is it was called a super SPECT, and it was supposed to be really good for hearts because again, what you do is you center the camera exactly over the heart, and there's some software that allows you to find the heart and get exactly there. And then basically everything is pointed exactly at the heart, and that radiation that's coming off in 360 allows a increased sensitivity, and it also magnifies the heart slightly so you get a little better view.
Since you increase the sensitivity and you magnify it, you're going to get less resolution, correct?
Yeah. The magnification here it's not as downgrade in resolution as you might think. It'll come down a little bit, but it's not a massive reduction in resolution. In this case, you might get a little bit less. We're going to talk about pinhole in a minute, and pinhole is actually really high resolution. So I'll show you the difference, but yes. Okay, so that's converging. Now pinhole is an interesting one to wrap your head around a little bit. So this is designed for very small organs, such as this will often be used for like a thyroid, or small bony joints like maybe the wrist, or you're looking at like navicular for a small hairline fracture, things like that. Basically what you have here is you've only got two main septa. So it's shaped like a cone, and both of these sides are either lead or tungsten. And then you've got a tiny little aperture at the tip, and most cameras come with the ability to change the size of this one tip. So this is going to have one borehole. That's it. One little borehole is all you're getting, okay? And that's usually somewhere around 3 to 6 millimeters, so very, very small. So the sensitivity of this goes really, really, really low because we're only letting 3 millimeter little hole through, right? It's tiny. So these have to be imaged pretty long to get what you need. But the image resolution on these is high. You might think, wait, how does that make sense? But the reason it makes sense is because you're only letting photons through that small 3 millimeter hole. What happens, and this is, again, takes a little bit to get your head around this, but if this is our object, we end up with an inverted image. And the reason why is because that's a tiny little hole, everything going straight through is going to get straight through in just that 3 little millimeters. Then for the rest of our image to form, it's going to only accept things that are at quite an extreme angle. So if this is our thyroid, that's, it's nice and hot with radiation, the left side of this going parallel photon is going to get blocked. A little bit less parallel, still blocked until you get this extreme angled one that will finally make it through that little 3 millimeter hole. When it does, though, it's going to go all the way on the other side of the image and be represented there. And that's going to happen all the way across. So everything that's on the left is going to go to the right, and everything on the right is going to go to the left. And then everything in the middle is going to slightly flip. But it's very high image resolution because, again, we're not letting much through. It has to be specific, even though they're angled, because it's such a tiny hole it's letting through, it's very, very accurate on that one bullet hole. Okay. Again, I know it's kind of weird to get your head through, but again, because there's no septa inside, those are allowed to travel and strike the camera all across. And you're going to get a very, very magnified image that is also very high in resolution because, again, only that tiny little porthole. So it's superior resolution. Again, I know that can be hard to understand, but that's how those work. And just keep in mind when you think about this one, just think magnified image, awesome resolution. Okay. So that's it on collimators. Any questions on collimators?
Bree's got a question in the chat.
I need to get my chat up. I don't see my dang chat. Where is it? Will you tell me that, or either Bree, speak up. If you don't want to speak up, Ashley, tell me the question.
So maybe this is just my X-ray brain going, but I thought that having a really, really magnified image, at least in X-ray, mean that there is less resolution. So I'm just confused that because it's magnified, it's not as sharp, I guess. I don't know.
Yeah. And usually, I would say you have to think about how you get a magnified view in X-ray. You're usually having to increase the distance, right? It is hard, and that's why your X-ray brain is having a hard time, because the way that resolution is formed in X-ray is not the same as the way the resolution is formed in nuclear medicine. The thing to just think about is that, again, remember that a small borehole, when we had septa, it blocked unwanted photons because we want them represented exactly where they are. In this case, though, but that's with many boreholes. In this case, because there's only one, you're getting, even though it's the one over here that's on a far angle, you're getting it represented perfectly exactly opposite where it would be, but it's still represented in exactly the right place. And same with every one along here. It's still going to be represented just perfectly opposite, and the image being bigger. So I know it's hard to think, but resolution in NewtMed is just representing something in the accurate place that it should be, not necessarily a difference between sharpness or fuzziness, right? When you blow up something in X-ray, you get a little bit of distortion and fuzziness. And again, your X-ray brains are probably more in tune with X-ray than mine, because it's been years for me. But that's the idea. I don't know if that helped or not, but and this one is the only case that's that way, particularly because, again, we're only letting through that one little tiny borehole, and so the the photons don't have any option except to be very precise in where they're traveling. Because that's the other thing to think is that X-rays, when they travel, even though X-rays travel in 360, whatever photon heads in a certain direction, it goes straight. It doesn't wobble around, it goes straight. It goes perfectly straight. So when you're getting the photon, it goes exactly where it should be along all of those things. I know it's kind of hard to wrap around, but that's the best I got for you.
I got one question. Just in this scenario, just so I can kind of understand a little bit more.
Yeah.
What would happen in the pinhole decollimator if you increase the distance from with the camera to the patient?
Yeah, that's actually a good question. So that would actually probably, it's gonna mess with your sensitivity, right? But it's also going to mess with your with what you can see, right? The closer you are, the more that object's going to be represented. But if you start pulling that away, I mean, I wish I could move this actually, because you could, if you pulled this down, what would happen is this, if we follow this exact dotted line, it would come clear down here. It would be no longer represented, and you'd have your image down here, but your spread would be less. So you'd probably have an actual smaller image, and it would probably be really, the resolution would probably go down as well. I've never been asked that question, but it's a good question. But just thinking through that, you pull it farther away, you're going to be able to see less of the sides. If you had it way down here, this angle is really, really severe, so it's going to go way over here. But if you pulled that down, then this angle would no longer hit the camera, and it would be a less steep angle. So you'd probably get a smaller picture. And again, one of the whole reasons to use a pinhole collimator is getting a blown up image that's detailed, like in the case of, hairline fracture on an navicular, or being able to view the thyroid. So that's just me thinking through it. I've never been asked that. So yeah, good question.
Okay, thank you.
Okay.
I have
Go for it. Who's got it?
So you say it will be projected as an inverted view. Does the camera or the computer flip it back to where it's supposed to be?
Yes, thank you. I actually, that's one of the things I usually mention, but yes, yeah. So your software, it flips the view, but your software will flip it back for you so that everything's accurate when you're looking at it. Yeah, good question. Thank you. Yep. Okay. Any other questions? Okay. All right. So that's detectors, or excuse me, that's collimators. That was quite lengthy. That's kind of our first thing that we get through. Now remember, we were going to follow the photon through. So now we're going to go and we need to talk about the crystal. To understand that, we need to talk about scintillation. So what scintillation is scintillation is the transfer of something from a photon energy to visible light. Okay, and eventually we're going to get to electrical signal, but what scintillation is when something responds with visible light. So scintillating crystals convert gamma rays to visible light. That's the idea. The crystals that are in your camera are made of sodium iodide, which is thallium activated. We'll talk about what that means, thallium activated sodium iodide crystal. Don't worry about that right now. Guarantee that's a question probably on your boards, but I'll explain what that means in a minute, but they're made of sodium iodide. Now on most gamma cameras, your crystal is about 1/4 of an inch to 1/2 of an inch thick, and it covers your entire head of your camera. Now, on a lot of graphics and books and things, when you look at it, we're going to talk about a photomultiplier tube next, but it almost makes it look in some graphics on books like there's a little crystal on top of each photomultiplier tube. That's not what it is. I actually had that incorrectly in my head when I was a student, and I had to like unlearn that and figure out the right way. But this camera is a large camera across or a large crystal across the whole head. Okay. It covers all of the entire head of the gamma camera. It's usually sealed in a reflective material because your crystal is hygroscopic, which means that it can absorb water from the air, and we don't want that. That can mess up efficiency of your crystal if it absorbs water from air. Again, this is almost guarantee a test question too, is you know, one of the understanding hygroscopic means absorbing water from air. And it's also heat and cold sensitive. So this is why most of your camera rooms are kept at a certain temperature, which is fairly cool compared to what we like as people. But they're heat and cold sensitive. So if they get too hot, they can stop functioning correctly. If they get too cold, they can stop functioning correctly. Although I would say your sensitivity is more on the heat side. And then again, they need to stay dry. Okay, so that's kind of your crystal. So in this next slide, I'm going to describe how scintillation works. I don't think you're going to be tested on this exact physics that I'm going to go over with you. I'm going to go over it so that you understand it. But I think generally you need to understand that when we talk about scintillation, we're converting gamma rays into light rays. That's what it does. So I'm going to explain how this works. Up till now, when we talk about electrons, we've been talking about things like in the K-shell, and we're talking about electrons and how they, you know, either orbit or in an electron cloud around the atom. I'm going to reference electrons moving when I give this part of the physics. I don't mean that they're physically changing locations. To understand scintillation, we need to talk about energy, the energy of an electron, okay? So in scintillation, the energy inside a crystal, the electrons within the crystal have different energy states. They get excited, and in those different energy states is how this works. So when I say the electrons move, I'm not talking about physical movement. I'm talking about getting more excited or less excited, okay? So in any solid state material like crystal, you have what are called conduction bands. And so you have the valence band, which is kind of low energy, and then you have the conduction band, which is kind of higher energy. And again, what we're talking about is the electron, the amount of energy that the electron is associated with the electron. So what happens is when a gamma ray comes and it strikes the crystal, that excites the electrons within the crystal. So they go up to a greater energy state. They go up into this conduction band, and they're in that conduction band until they calm down and go back into the valence band. Now, when they get up into the conduction band and they come back down, they usually just go straight from the conduction band back down to the valence band. Now, I talked a minute ago about that these are thallium. They have thallium in them, right? They're thallium activated. What the thallium does is it introduces a little bit of impurity to the crystal. A pure crystal, the electrons will come up to the energy of the conduction band, and then they drop back to the valence band. With that impurity of thallium, what happens is when they get excited, instead of going all the way to the conduction band, they go up to what they call this forbidden gap. So it's like this middle area. And when they come down from the forbidden gap and they lose the energy, that energy comes off in the form of a visible photon or a light photon. If we didn't have that thallium in and they went to the conduction band and came back down, it's not visible light that comes off. We wouldn't see it. I honestly don't even know what the energy transfer is there. But with the thallium, it comes off in the form of visible photons. So again, it's excited electrons. They calm down a little bit, and visible light comes off of those electrons. That's what's happening in scintillation. This actually is the same thing that happens when you learned I know a lot of you probably mostly work with digital with X-ray, right? But back in the days of film, inside your film cassette, they had some, I don't know, was it thallium? Is it thallium or sodium iodide? I don't even remember now because my X-ray brain's long ago. But the same thing happens in there. When an X-ray strikes it, you get lighting up of that, and it exposes the film, right? So same idea. Here we've just got a crystal that gives off the light. So that's scintillation. And again, I'll point out I put the photoelectric effect here because again, every gamma ray that comes in, if it's completely absorbed, which is what we want, the gamma ray coming in represents a certain energy, and a certain amount of light will come off from that energy, and it's the same every time. So 140 keV coming in is going to give off the same intensity of light every time. So this is important because we have to keep that proportionality as we go, again, from a photon to light and all the way to electrical signal eventually. So that's what I have written here. So and I have the number written. So 140 keV photon will emit about 3,000 visible light photons, right? So intensity. And so something with greater, like I-131, 364 keV, it's going to give more light photons off. Okay, so it's proportional. Okay, so that's scintillation. The next thing that comes along in our line is the photomultiplier tube. Okay, so I've got this right here. You can come back and look at this. I'm going to go to the next picture or to the next thing because it's the graphic. It's just easier to look at. And I'll explain what's on this page and I'll explain what's on this page just while we look at this graphic. Okay. All right. So, okay. So in a photomultiplier tube, the photomultiplier tube is what is responsible for changing that light photon that came off the crystal into an electrical pulse that we can now start to use, okay? So what happens is there's a thin alloy. There's different types of metals that are used right here, but it's a thin alloy that's light sensitive. And what we mean when we say light sensitive is it means that when a light photon strikes this alloy, it will actually kick off an electron, okay? So when light strikes that, it's sensitive. That's what light photosensitive means, is it kicks off an electron. What happens within the tube is when that electron is kicked off, we'll pause it right there for a minute. You have these kind of snake-looking thing. What these are called is dynodes. These curved guys right here, they're called dynodes, okay? And there's typically about 8 to 14 dynodes within a photomultiplier tube. But what happens is you have in the photomultiplier tube, this is very similar to an X-ray tube. You have your cathode side and you have your anode side. What that means is that when you put an electrical voltage across there, it has a pull, right? So things are going to be pulled from the cathode side to the anode side, okay? We call that a photocathode because it's that alloy is photosensitive or visible light sensitive. So when that electron gets kicked off because of that voltage or that pull, that electrical pull, it's going to be pulled at a high rate towards the first dynode. When it strikes this dynode, it's going to multiply and maybe one electron usually kicks off 3 or 4 or 5 electrons. So it'll kick off several electrons. Those will be pulled because of the voltage to the next dynode, which then those 4 electrons are going to kick off 4 each, right? And you're going to have this multiplying effect for each time it hits this dynode. Eventually, when it gets to the anode side, you're going to have this pulse or this electrical signal that's big enough to be seen, right? So you have this electrical pulse. So what we've done is we've gone from visible light through the dynode process into an electrical pulse. And so on the next slide, I've kind of listed how that happens, okay? So you have the light sensitive photocathode, kicks off an electron, electrical field pulls it, multiplies multiple times. This was repeated about 18 to 14 times in a cascade event that amplifies the original electron to about 10 to the 8th power. So you have a lot more electrons, and that's how we get an actual signal on the other end of our photomultiplier tube. Now, I found a cool video online, and I'll try to play it here. Sometimes it works well and sometimes it doesn't. If you're watching on like a phone or something, it's probably not going to work well, but pull it up later on your computer and you can do it. It's a cool animation that kind of takes you through this. So I'm going to hit play and hopefully this functions okay over Zoom. Okay, so here's our tube. We got our photocathode here at the end. We're going to see this light photon. That's a light photon. Boom, it hits. Now we're an electron instead of a light photon. We come in contact. First dynode, we multiply, second dynode, and you'll notice that those electrons are multiplying. Now this is not to scale, obviously, but you're getting this multiplication effect. What that's doing is it's going to produce, when it hits the cathode end or the anode end, you're going to have an actual pulse, electrical pulse that we can use. Okay.
So how does an electron hitting the dynodes actually multiply the amount?
So that electron is being pulled by voltage. And when it strikes, it has a reaction of kicking off electrons. It's actually hitting the electrons within that metal, and kicking them off, just like a lot of the reactions that we have with, with other, when we talk about scatter radiation and different things like that, is kicking off electrons from the middle.
So does that mean those tubes have a certain lifetime then, because they'll eventually run out of electrons, or are they able to pull electrons back into the metal?
That's a good question. I honestly I've never been asked that, and I don't know the exact answer. I do know that photomultiplier tubes do get traded out. They don't last forever, and that could be why.
Well, if you think about like an X-ray tube, like when it hits that tungsten, the same, aspect hits, the electrons come off. And so at some point those tubes need to be replaced because the life of it is gone, right? There's less and less electrons being able to hit off.
Yeah.
So I was just wondering if it was the same concept.
And this is similar. I mean, with X-ray, kind of a similar idea, although there you have thermionic emission, and then that, those same idea, though the electrons get pulled over and strike, and then you get a reaction there. So this is similar. It's just that it's probably a little less powerful. This is next thing we're going to do is talk about two different amplifiers that this electric signal goes through. So this is very much less powerful than your X-ray brains thinking of that X-ray tube, which is high energy, right? Because you're producing X-rays. Here, we're just kicking off a few electrons. So again, I love the way your brain's thinking, and I'll look up that answer. I've never thought about it, but they probably last a lot longer than your tungsten on an X-ray tube, because again, this is really small. Again, it's just one light photon and then one electron that starts this process. So the short answer is I don't know. I've never been asked that, but I would guess that they last quite a long time. But yeah, it's a good question. I like the thinking. Probably not on your test, but I like the thinking.
So if that won't age out a gamma camera, then what ages out a gamma camera?
They still get changed out. I don't know the answer to that really. I think what ages out a gamma camera faster than anything is that new technology comes, and everybody wants the latest and greatest and better way to get imaging with less patient exposure and better images. But yeah. Okay. So here's kind of how your photomultiplier tubes are stacked on your camera. So this little square right here represents the crystal. And so these would be just under the underside of the crystal, all stacked in kind of this type of a configuration. A lot of cameras have circular photomultiplier tubes, but you can have hexagonal. You can also have square. They can have a slightly different shape to them. But this is the idea that they're all lined up on. Okay, so I did want to mention this. When we go through that dyno process, I mentioned that you get this pulse at the end. This is important because we're going to kind of go into what photopeak is, but the current reaching the anode is recorded as an electronic pulse, like I said, and the energy of that electronic pulse is termed photopeak. So when we say photopeak, we're gonna look at this a little later, but it means what is the energy that's being read? And what I mean is things like 140 keV, that kind of stuff. Okay, so when we talk about photopeak, it comes out at a certain energy, and again, depending on, remember how I mentioned that tech is going to throw off a different amount of light photons from the interaction of scintillation in the crystal than I-131 or something else is going to throw off. Okay, so when you have more light, you're going to end up with a different peak at a higher energy level when it comes out at the end. Okay. All right, so we need to talk about positioning logic. So the other thing that photomultipliers do, besides record that energy pulse and keep it the same from beginning, again, we have a proportionality all the way to this energy pulse, is that they also do the positioning logic of where something happened. Now, we already talked about how a photon is coming through, and it comes through boreholes and it strikes the crystal in the right place, right? Within a little bit of 3 or 4 millimeters. So it strikes the crystal in the right place. So the question is, how does each photomultiplier tube, because again, they're a lot bigger than one single borehole, how do we determine, or how does that crystal know where that, not the crystal, excuse me, how does the photomultiplier tube send an electronic signal to tell that where the position of that was? And that's, the photomultiplier tubes do that. And this is the way they work. If you can imagine your camera remember back to your math days when you did X and Y coordinate stuff, right? So if you can imagine that your camera head, or the crystal maybe is what we'll say, has an XY coordinate right on top of it. So the very center of your camera head would be 0, 0. And then you have X and Y coordinates going out with positive and negative coordinates, you know, negative down, positive up, positive right, negative left, okay? So what happens is instead of just one single photomultiplier tube, like let's say the event happens over a single photomultiplier tube, that photomultiplier tube will see it. But what it does is, remember, I talked about how light, X-rays, gamma rays, any kind of energy spreads in 360. So when a crystal is struck, you're going to have an intensity of light right where it's struck, but the entire crystal is going to light up to a certain degree, with the greatest degree of light being right where it's struck and lesser degrees of light as it goes out through the entire crystal. So what happens here is that the photomultiplier tubes all are watching for an event. And when an event happens, every photomultiplier tube sees that event as some pulse of light. And then what happens is they take the signal strength that each of those photomultiplier tubes have, and they coordinate with each other and say, okay, who saw it the strongest? And so you'll have a photomultiplier tubes out towards the end. They'll be like, well, we only saw this intense of light. And as it gets closer to the point, we see where the most intense light was seen. And what the photomultiplier tubes are able to do is sum that energy or that intensity together and determine exactly on the XY coordinate where that took place. So that's done by the photomultiplier tubes. And so that pulse at the end that comes out, not only does it have an energy level or how big of an energy came out, but it also saves, because of the coordination of all the photomultiplier tubes, where that XY coordinate happened, okay? So it saves the intensity, how much of it saw, and the position or the XY coordinates. And maybe that, so yeah, if you look at this, maybe that's an easier way to explain it, is 0, 0 would be right in the middle, and then you'd have X coordinates going both directions and Y coordinates going both directions. So if this tube is where the energy struck, then all of these tubes would see a little less, all of these would see a little less, all the way out to a little less. And so as they coordinate with one another, they're able to know exactly where that struck. Okay. All right, so I brought this up because it kind of puts us back to, again, following our path. So we, through the crystal, through the photomultiplier tube, the next step is going to be the pre-amplifier, the amplifier, and then we'll talk about the pulse height analyzer. So preamp, what it does is it just boosts the signal 4 to 5 times. It's actually connected right to the back of the tube so that there's no loss in signal. Because again, that pulse that comes out is actually still really, really, really weak. It's just very tiny signal. That preamp is going to boost it and help it be a little bit bigger. And then after that, it travels and hits the amplifier. So the amplifier, again, also is going to boost it again. And it boosts it about 8,000 times. It keeps the proportion of energy, but it takes whatever it sees and it boosts it about 8,000 times. The other thing it will do is it will, you're seeing it as a pulse. It will slightly shape the pulse so that it is a little bit more symmetrical. And then it continues to carry that X and Y positioning and the intensity of what it saw. So it'll do that. It'll kind of keep all of those. So once you get through the preamp and the amplifier, then you're actually finally to like an electronic signal that's usable. So that's why I say when we have that discussion about the diodes and the things going out, again, I don't know the answer, but I know that we're talking about such small amounts of energy beginning. We have to amplify it by 8,000 times to get just a basic electronic signal, okay? So that's the preamp and the amplifier. Pulse height analyzer is the next thing that we're going to talk about. And I'm going to kind of read this and then we'll look at the graphic because it's a little better at explaining it. But the basic principle of a pulse height analyzer is to analyze that pulse or that photo peak and disregard signals from background and scatter so that only primary photons known to come from the photo peak of the isotope that we're looking at are imaged. Now I know that I want that there and I wanted to read it because as you learn this and you go back and read that sentence, it's actually a really good description and it will make more sense. Let's go through and talk about it, but that's what it does. The reason that a pulse height analyzer can make the discrimination is because the energy deposited by a photon bears a linear or proportional relation to the pulse that emerges out of the photomultiplier tube. What do I mean by that? Remember, we started with a certain energy gamma. We took that through and we turned it into light, and it kept everything proportional. And now the pulse height analyzer is going to be able to measure it and look at it and analyze it and now tell you what energy it's seeing. So in other words, you started over here, you know that you're using tech and you know you're giving off gamma rays at 140. That pulse height analyzer is the thing that's finally going to look at the signal and be like, yep, I see 140. It is 140. And then not only can it analyze it and see it, but it's also going to be able to be like, okay, now let's clean it up a little. And now we can specifically say, I only want to look at 140. Anything else that happened during this process, little extras, we're going to get rid of them. Okay, let's look at pictures because it's just easier. Okay, so on your camera, and you should ask your tech to show you this if you already haven't seen it, but on your camera, when you put a patient under the camera, you should have a spectrogram, what's called a spectrogram. And that's what you're looking at here. It's going to show the photo peak and what energy it's seeing. So on a spectrogram, you have the number of pulses. This is kind of the number of electronic signals. So what it's seeing the most of. And then this is the energy of the pulse in keV, right? So when we look at the energy, this is determining where along this we see the energy. So we would expect that we would see tech somewhere in the 140 neighborhood. In this case, we're looking at cesium 137. So we're seeing a keV of 662. Okay, so this is telling us the energy, or this is what we mean by pulse, the pulse height, the energy pulse. And then this is how much we're seeing. So if we took cesium and we put it under a camera and we brought up our spectrogram on our camera, this is what we would see, and we would notice, okay, look, we've got 662 keV. Even if we didn't know it was cesium, we'd be able to identify because it's 662. We'd say, oh, we have a ton of that. This is obviously cesium. This is obviously what we're seeing, right? As cesium, and that's what it would look like. And this is what we call a photo peak. Okay. Now you'll notice a bunch of other stuff in here, and that's because, again, as we're gathering our data, we can still experience some scatter and some other things that happen. And I've kind of represented those down here in this graphic. So what we love, again, is that photo peak full absorption. So if a photon comes in, strikes a crystal, and we've got total absorption, that's awesome. Sometimes you can get a little bit of Compton scatter even in your crystal. You can also get some characteristic and scatter from the septa. If things hit, they're designed to absorb as well, but you can get some scatter. You can even get where you have an absorption or two photons that hit a crystal like exactly the same time. And so you get this like kind of multiple absorption that can kind of throw off the energy and make it look like it's higher energy. And so there's things that can happen in here. And that's what you see here. And all this other stuff like this Compton edge and Compton Valley, this is a little bit of Compton that's created because of this high energy. And you can imagine that the nuclide with higher energies are going to create a little more scatter, Compton, and things that happen within the system. This one over here is interesting. You have this barium 137. The daughter of cesium 137 is barium. So what you're actually seeing right here is some decay into the daughter product happening. And so when you stick cesium under a spectroscope and you look at the whole thing, you get this 32 keV right here that's coming off in the form of an X-ray from barium. So again, every nuclide that you look at is going to have a different photo peak. It's going to look different, but you're going to see most of the events or the pulses where the majority of that photo peak is, right? But again, with slight variation. Now, this next, the next thing that we talk about, again, that's the analyzation of that pulse. Now, here's the other thing that the pulse height analyzer does is it's able to do some discrimination and help us with our image. So it has what's called an upper level discriminator and a lower level discriminator, okay? What happens here is you have the lower level and the upper level, and you can move and change these. And essentially what this is for is you're going to identify and tell the camera, okay, I only want you to look within these certain energy ranges, okay? And so usually you'll have a window, like for tech, usually there's a 20% window set up, which means there's about 10% above and 10% below. So right in the middle, or the photo peak, you're going to have 140 keV, and then you're going to have like 10% going up, I don't know, like 155 or whatever it might be, and then you're going to have 10% going down. And so you're going to allow a little bit of that to come in. Now, the reason, again, you would think if we've kept everything proportional, you would think, okay, well, shouldn't there just be one single line of 140 and that's all we see? And again, the reason that it's a little bit of a spread, it's not a perfect peak. It's kind of like a, similar to like almost like a bell curve type of thing. And again, because of what I talked about here, it's not a perfect system, right? We want it to be a perfect system, but it's not. And this idea is what we call energy resolution. Remember when I mentioned at the beginning energy resolution, and I said the ability to go from that gamma all the way to energy that we can look at and identify, right? So the idea of the camera here is we want this photo peak to be a pretty narrow. If that photo peak started to get really wide and weird, that would mean we're accepting energies and we're seeing energies and something's happening to where it's not resolving it, right? So energy resolution is the ability of the camera to be able to see just the energy that it's trying to see. That's why I said it doesn't make sense when we say resolution in like an X-ray brain where we're just talking about an image. We're just saying, can the camera resolve and only see the energy that it's supposed to see and see that accurately and create it? So if anywhere along the system from the gamma all the way through the crystal and the photomultiplier tube, if those things aren't functioning correctly, then it's going to change the outcome of that pulse and what it looks like. And so what we want to see is a very narrow pulse that only sees what we're trying to see. And then on top of that, we can set that window to where we only see what we want to see. We can just say, hey, discriminate everything else that you see. Now, usually they set the window in center, but sometimes that's called a symmetric window, but you can also have an asymmetric window, meaning that you might shift that window to the higher side of the energy or the lower side. And the reason that you would do that is there are some nuclides, and I'll go back to here. There's some nuclides where this Compton Valley on cesium-137 is separated, but sometimes you can get that Compton Valley right on the edge, and it pushes into the photo peak here and causes this big wide thing out here. So in that case, you could take those upper and lower discriminators and you could shift it in the direction you need to cut off that Compton Valley because it's erroneous data. We don't want that energy. It's not going to help us, right? Most of the time you're going to see symmetric. Technetium is a symmetric window. But again, go and talk to your techs if you haven't already seen this. Usually on the camera somewhere when you're setting up your patient and you're like kind of control station for the camera, you can find the spectrogram and you can look at the photo peak. You can see what you're actually producing. And so I would recommend doing that.
So quick sidetrack here.
Yeah.
Is that how a well counter works? Like when you're doing the well counter, you can click between all the different isotopes and it's just changing the photo peak. So like if you just happen to have technetium in the well, but you happen to be on like cobalt, it'll still pick up some of the radiation, but it's not the correct reading.
No, I can see why you say that. It actually just applies. It actually just applies a factor, but it's not shifting the. It doesn't have like an upper lower discriminator. It's not shifting anything. It's just seeing energy in general, and then it just applies a factor based on when they set the machine up. It just has a factor that it changes. It's a multiplication factor, so it will see energy. And it'll say this much energy. If you're telling me it's tech and there's this much energy, then this is how much it's going to be. If you're telling me I have cesium and I see this energy, that's how much it's going to be. So in other words, if you put cesium in there and you hit the tech button, it's going to be really, really high number. So it's not exactly the same. It just has a multiplication factor depending on, and that's something usually set up by like the physicist or whatever. But I can see why you think that. I like your thinking. All right. Okay, so we're almost there. Let's get through. So again, this is kind of the same thing that's in the other picture, why we don't have just like a straight photo peak. So we talked about full width half max. I don't think you'll be asked to figure one of these out. You're not on my test, and I don't think they put this on the boards. You could see one of these maybe in some of the practice tests that you'll see in summer with the review book we use. So I don't want you to be overstressed on learning necessarily the equation here, although the equation isn't super hard, but more with understanding what we mean when we say energy resolution and what full width half max is and how it works, okay? So what we see here is a photo peak, okay? And down here we have our KEV range, and then again, like the number of events. So what full width half max does is it's a way of measuring the spread. I remember I mentioned a minute ago, we want our photo peak to be narrow because that tells us we're closer to only seeing the correct energy that we want to see. As it starts to spread out, that means something's happening in our camera that's erroneous and making it so we're seeing way too many energy values when we should be seeing that one. Okay, so this is a measure of that energy resolution. This is the QC that tells us our energy resolution is good. So the way it works is you have your maximum pulses, okay, and your half maximum would be just go halfway down your peak here, and you find that number. So in this case, on the maximum, it saw 1,000 pulses, and down here we're seeing, or excuse me, if you go halfway down, that's 500. And then what you do is you measure the energy width at that half maximum, okay? So the energy width, so in this case, you come down here and it's going from 132.5 keV to 147.5 keV. So you take that amount, which is 15 keV worth, right? If you say that how many keV is in between these 2 points, it's 15 keV from 132 to 147. Mathematically, it's down here. You could take 147.5 and minus the 132.5, and you end up with 15 keV. Okay, so that's your width. Your width is 15 keV. Again, if that thing went out wider, you'd be getting a wider width of keV, but in this case, we're 15. Okay, so then then what you do is you take this equation, and you're going to take the full width half max keV, which in this case was 15, divided by the keV of the photon energy. So this would be where you're at in the middle, the peak, right? 140. We're looking at tech. So you take the 15 divided by 140, and then you multiply that by 100 to get the percentage. And in this case, on this graph, we're getting 10.7%. So your whole full width half max on this graph is 10.7%. For technetium, a good full width half max that tells you you've got good energy resolution is between 8 and 12%. I put cesium on here just for reference because we were looking at that. Cesium is a 7 to 9%. These are things that you would look up. You're not going to need to know the percentages of full width half max for any of these. What I want you to know is, what is full width half max? What am I doing? Well, I'm measuring the spread of energy and understand that I want that energy to be narrow, not wide. So I'm measuring the spread. And then again, just understanding that this is how they get that energy spread and how the quality control we do to look at it. Okay. So that's full width half max. Now, I've debated on how to do this for years, and I've switched it around back and forth. But we use full width half max for spatial resolution. Right now we're in energy resolution. I'm going to jump out of energy resolution and just show you the spatial resolution really quick. And I'm only doing that because I just want to put full width half max in one spot. But just remember, with full width half max, you have energy resolution, which is, we're looking at our photo peak and measuring the spread of energy. And then in spatial resolution, we're looking at the spread of, oh, and here's another, there's cesium in more detail figured out. We're looking at this, the spread across our camera of spatial resolution. So let me hurry and show you that. If this screws you up, just separate the two and look at this one on its own later. But spatial resolution is a measure of the spread of gamma events across your camera head, okay? So I mentioned before that gamma cameras have an inherent spatial resolution of about 3 millimeters, okay? So this is a similar idea, and what you're seeing here, I try to put this, I like this graphic because it kind of shows you your camera head. So if this is your source of radiation and then this is your camera head, what you should see is that you should see most of the energy right here in the middle, right? Because that's where it was represented. You don't want to see a lot of energy out toward the edges. You only want to see the gamma event right where it occurred, right? That's what we talked about. Resolution on a gamma camera is representing an event right where it occurred in space. And so when we look at the energy coming off of a gamma camera, we get this pulse. And again, we want to see most of the energy here. And if you can imagine, same principle applies. we want to see most of the counts right in the middle where it occurred when we get our image across the crystal. But if it starts to spread out and we're seeing a lot of activity across the crystal, that means it's not getting good spatial resolution. Again, we want that to be right down the middle. So this is measured in the same way. You take that, so this would be your count, number of counts, and then this is distance from the center of the crystal. So this would be 0, and then we're going distance positive x and distance negative x from 0. Okay, and that just represents where on your camera it's seeing activity. So you would take that 0 distance, you would look at the full maximum counts, you would go to half of those counts and then measure the spread of what's happening there. Again, we want that spread to be narrow because we want what's happening in a radiation source to be represented right where it said. If our camera is seeing that event spread clear across the camera head, then something's wrong. It's whether you got an issue with your collimator, an issue with your crystal, something's happening where that spread is way too wide. We want that spread to be narrow. Okay. So that's again, they'll do your physicists that come in will use full width half max. And what they do is they have it's like a long bar phantom, and they hang that up above your camera head. And so it's spreading light down on, or spreading gamma rays down onto the whole camera head. And then again, what you want to see is it represented right in the middle where that actual phantom is, and less along all the other edges of the camera. Okay, but it's, again, math-wise, it's figured out the same way with full width half max. Okay, so sorry to pop that in there, but I found that it kind of works to at least get full width half max out of the way all at the same time. Okay, all right. So what I want to do now is kind of we followed everything through, and now we're going to start making a picture. Okay, so the pulse type analyzer is kind of the last thing. Remember, it kept the energy level, it kept the position of where it happened the same, and the intensity, and we know what we're looking at, and we've gone through that pulse type analyzer and said, okay, this is what we want to see. So now we're ready to start forming our image. Now, before we start talking about this, I'm going to take just a quick little. I'm going to pause for just a minute because, again, we only have about 10 minutes left of actual class. Sorry, I think I've just been too yappy today. Normally can get through this in 2 hours. But again, stay as long. I'm going to go until I'm done. Stay as long as you want. If you need to go, totally cool. Okay, and I'll make sure everything's done. All right. So let's start talking about our image display. So the most common way of acquiring on a gamma camera is what we call matrix or frame mode. We'll kind of talk about the difference between those two. But matrix, when we talk about the matrix, it's basically a parameter that determines the number of pixels that will be used to acquire the study. Now, I know as soon as I say pixel, you guys are thinking about your computer screen. I'm not talking about your computer screen. That word pixel stands for picture element, okay? So what this is a grid or a matrix laid right, if just imagine laying this right on your camera head. And so each of those pixels on that grid is just a representation of a place on your camera head, okay? And those matrix sizes are bigger and smaller, okay? Higher matrix sizes have an ability to record fine details because they're smaller picture elements. And so we get better resolution there. If we have smaller matrix numbers, so we end up with bigger bigger pixel sizes, then we get areas that they don't record quite as fine detail. So, and they keep the X and Y position. So that's what you have on this graph. If you look here, when that pulse type analyzer analyzes it, you've got the X and Y coordinates that are all divided up among these pixel elements. So again, that's why it'll on the photomultiplier tube, when the crystal has light, the photomultiplier tube sees the energy. They all decide together based on light intensity where it was, and then that's where the camera places it on the X and Y coordinates within a matrix like this. Okay. Now let me give you this is kind of a better graphic to look at it. But it's basically like a square mosaic that's laid right on the crystal head, like I said, divided into blocks. Each block is one of those picture elements, and we can tell the camera to look at this in different sizes. We can use different matrix sizes. So common matrix sizes here that you're seeing right here are like 64 by 64, 128 by 128, 256 by 256. Now, keep in mind, again, when we use a smaller number, we get these smaller amount of pixel elements, but they're bigger in size, okay? So 64 by 64, you have 4,096 picture elements. By the time you get to 256, you have 65,536 picture elements. So again, we get more pixels or picture elements to work with when we use a bigger grid. Now, each time a detected event occurs, the number of counts on that picture element increases by 1. So that's how we start to form our image. All of you guys have sat there and watched an image form, whether it's a bone scan or a height or whatever, right? You put them under there and you start gathering. And so each time a photon hits, it records it as an event within whatever matrix it's in. And so more photon events are going to get brighter in that particular pixel element. Now, the reason I put these numbers down here is because these graphics are terrible. Like, this is huge, right? Your picture elements are not this big across your camera head. It's just I couldn't make them small enough to be accurate, right? It's just a representation. But again, remember, our picture elements, the size of them, you can get down to like 3 millimeters. And I gave you an example of a size down here. So if you had a 40 centimeter field of view and you were using 128 matrix, right? Each pixel would represent 3.1 millimeters. And the way I did that is I just took that 40 centimeter field of view would be 400 millimeters, right? So in this case, I did millimeters. 400 millimeters divided by 128 pixels is 3.13 millimeters per pixel. Okay, so these are very small when you're at 128, and they get even smaller when you're at 256, right? You get very, very tiny. One thing to try to understand with matrix and why you would use different ones in different scenarios is, remember, when we acquire, we have to get counts to form an image. So if you make your pixels really, really tiny, then you're going to have to acquire a lot longer to get each pixel to have enough counts in it to represent something on your computer screen, okay? Whereas if you have large pixel elements by using a smaller matrix number, you're going to have a lot more events happening quickly within that larger amount of space. This is why, for example, and hopefully Brandon is talking to you when you talk about each type of exam you do. He may mention matrix sizes, and the reason why you would do that, just to give you an example here, usually you'll do a bone flow on a 64 by 64. Why? Well, because you're trying to catch the flow live as it's happening, so you don't have a lot of time to sit there because it's moving through quickly. You need to gather the data, a lot of data quickly. So a 64 by 64, because the picture elements are bigger, as that flows through, it's going to grab enough counts to form that pixel. Whereas if it was a tiny, tiny pixel and the bone flow went through, it'd be like, I got 2 counts off that. It's gone. I don't see it anymore, right? It's gone too fast. So you have to use a 64 by 64 on something like a bone flow, whereas on a bone static, you might be using like 128 because you're just sitting it under there, you're just gathering forever, and those pixels are going to, all individual pixel elements are going to be able to gather enough data, okay? So that's your image matrix, and again, why you would use the different sizes for what you're gathering. But essentially, that's going to then transfer and represent exactly what you see on your screen for each pixel element is going to transfer to onto the screen. I mentioned a second ago on the previous slide, there's kind of 2 modes that things gather in. One is the frame or matrix mode, and then another one is list mode. So matrix mode is what I just mentioned, which is where each image pixel records the X and Y place and gathers based on how many counts it's seen. List mode is a little different. What it does is it takes everything that it sees in each pixel, and instead of just immediately putting it on the screen, it records it in basically like an address, and it lists each thing that happened in time on a certain address. And so this would be things like a bone flow is often acquired in a list mode, and the reason being is, again, you're trying to see something moving, and what a list mode allows you to do is it allows you to say, okay, I want everything that happened in the first 5 seconds, then in the next 5 seconds, and then the next 5 seconds, and then the next 5 seconds, because it's taken all the data and put it in a list and recorded it that way. Another thing that's recorded in list mode is in cardiology. we'll hook you up to a 3D EKG when you do a stress test. And then what that EKG is, it will watch the contraction of the heart from systolic to diastolic, and it will record what it sees in that list mode. And then you can then get what's called an ejection fraction. You can say to the camera, only show me systolic and then show me diastolic. And then I want you to compare those two and tell me how much contraction happened, right? We can do that because we've required it in list mode, and we can tell the camera which data we want to look at, okay? So those are kind of your two modes. Frame mode, again, is just acquiring on the matrix as counts happen. List mode puts them in a set of kind of digitized addresses, and then for recall, depending on what we want to look at. Okay, so that's pretty much the general gist of how the Gamma camera works. The only thing we have left now is we're going to briefly talk about how SPECT works on a Gamma camera, and then we'll cover a couple of quality control things. So SPECT stands for single photon emission tomography. Why they chose that, I don't really know. I guess they were trying to describe each photon hitting the camera. I don't know, but that's where we get SPECT from. SPECT basically uses tomography, and what we do with SPECT is we require at 360 degrees, or sometimes depending on what we're looking, if we have two camera heads, it may be 180 degrees. Or when we do L mode on a cardiac, we only go 90 degrees. But you're acquiring around the patient, you're acquiring static images, and then you're going to take those static images, we're going to combine them and create a reconstructed image that we can then break up into slices or view as a MIP or a 3D image, okay? Originally, you had single head cameras that did this, and so they would have to go all the way around the patient, each camera head taking a picture, stopping for a while and taking a picture. When you got the dual head cameras, then again, you only have to go 180 degrees all the way around. And then I mentioned too that that when you can use L mode for cardiac, the reason that works really well for cardiac is because when we do cardiac images, we're interested in the heart, which is all on the left side, and specifically, we're imaging the left ventricle. That's the main thing you're looking at when you do cardiac studies, is the left ventricle. Because of the way the heart sits to the side here, the anterior portion of the heart is kind of out at an angle from your body. And so if you have a camera head that's in an L mode, if you start out at the top, this side of the camera is looking all the way into the septal side of the heart, and this side of the camera is over towards the anterior. And by the time you just simply go 90 degrees, now each camera head is covered all the way back to the back side of the septal. So you don't end up needing to go 360 degrees, and you can still, or even 180, and you can still get a good view of the heart. So that's can be used in L mode, again, for cardiac studies. There's a couple of different acquisition modes when it comes to SPECT. We can do step or shoot or continuous, meaning that the camera stays in one position for a while and then moves. That would be step and shoot. Or there are modes in cameras that can actually just slowly, continuously move the whole time and gather the data that way. Both work well, and you probably most of the cameras, I think modern cameras can do both. Anything else I want to say here? Okay, that's the general gist of what a camera is doing. It's gonna get pictures from all angles. We also have the cameras can do a circular orbit, or some cameras can do what we call a body contour orbit. A circular orbit would be where you just come in, you bring your camera in close to a fixed position, and then it does a perfect circle around the patient. Body contours, which most modern cameras have, is usually two rails on the side of your camera that give infrared light across. And what will happen is the camera will adjust down until the patient body breaks that infrared signal. So it won't touch them, but it'll get as close as possible. And like we talked about, that can give you a way better resolution when you're doing SPECT, because again, the closer we are to our patient, the better resolution you get. This doesn't always work well depending on a person's body habitus and what's going on. If you're doing a heart and they have a really big belly or something, it might keep it out too far. So, patient habitus always determines kind of what you can do. But if you can use body contour and have your camera get as close as possible all the time, then obviously you just are going to get better images. Okay. Okay. So that's kind of like, I didn't go deep on how it works. That's the general gist. It's really everything that the Gamma camera does, but we're taking pictures all the way around the body. So the important part to understand really about SPEC, besides just that general acquisition, is how does this work? How do we take a bunch of separate images and then we get an image that's combined together and then that we're able to view as either 3D or reconstruct and break into slices. And so there's two main ways that we construct. The first one is filtered back projection, and the second one is iterative. I'm going to show you some details about filtered back projection, and then I'll kind of mention iterative. Iterative is not one that you have to understand in detail, just in a basic way, but I'll show you both of them. All right. So the way filtered back projection works is each image is acquired at a different camera angle, right, as you go around. Each of those camera angles is what we call a projection, okay? And each projection is divided in axial slices according to the matrix size. What do I mean by that? Well, if you imagine your camera head and it has a bunch of pixel elements on the matrix, each one of those pixel elements going across is going to be how many recorded as a slice for reconstruction, okay? So each one of those is going to be its own projection. Back projection assigns values to the projection to all points along the line of acquisition and then projects them back across the image plane. Now that probably meant nothing to you when I said it, so let me try to explain it in a more layman's way. This represents a person right here, and this little dot represents, like, you know, some radiation, whatever. Maybe that's a gallbladder. Should be off to the other side, but that's okay. And so what you're seeing here is the two camera heads, okay? And what's represented back here behind the camera head isn't a real thing. It's just representing like the energy it sees, or the amount of radiation. So you'll notice that this camera is seeing a lot of radiation right where the radiation obviously is. And then, as you guys know, you've put injections into your patient, and you see a gallbladder, but you still see some radiation throughout, right? So that's what you're seeing here, is a little bit of radiation throughout the body, but the most important right through the middle, okay? So the camera's detecting that as it goes around. And so it goes around and gathers that all. When it goes to do the reconstruction process, it takes that intensity of gamma rays that it sees, and it throws the entire intensity across the matrix, along the whole plane of the matrix. And it does that for every angle, okay? Every single angle, all 360 degrees. And what you'll notice as you lay more and more of these over, the area that had an intense amount of activity is going to become more it's going to become more and more hot, and it's going to show up the best. Whereas areas that didn't, while they overlap and increase each other, they're not going to increase at the same intensity level of the actual place, or the actual area where the activity increases. So we would say that as the number of angles increases, the back projection improves. The image becomes more and more visible because we get greater amount of counts in that one spot where everything crosses over, okay? This is the representation of like a body, but you just review it to think of it more of like a phantom, right? So we've got this phantom, and we're just going to break this into only 3 slices. Obviously, you'd have the matrix, you'd have a lot more projections or slices going through. So if we took this top slice and we just laid it on its own, that's what it would look like. As we took this next slice down, it would look like that, and the next one would look like that. What the camera does is it takes each of those slices, which again represents one line on the matrix, and it records in list mode each of those slices in one place. So it's going to take one slice and record all the data for just one slice or one projection, okay? And we call that a sinogram. So what you're doing here is essentially, if you were to take this top slice, okay, and we'll look at it down here. So say this is divided up into 3 slices. If you took this top slice and you placed it down here, it would be this first layer of this sinogram. And then you take the top slice of the next one and you put it on the next, and it would be the next layer. The next one would be the next layer. The next one would be the next layer. And so you're stacking that one slice all the way up in what we call a sinogram. And that's happening for the next section and the third section. Okay, so you're stacking all of these up individually. And that's what you call a sinogram. So that's how it's stored. So we gather the data, we store it, and now I'm going to show you a automation or an animation of how it reconstructs. And hopefully this brings together all the garbly goop I've just been saying, because I know it's sort of confusing at first. It took me a while to understand how this worked when I was in your position. What I'm going to do is I'm going to read these bullet points, and then I'm going to show you the video, and then I'm going to read them again, and I think it will click in at that point. So back projection assigns values in the projection to all points along the line of acquisition. It then projects them back across the image plane. This is repeated for all acquisition angles, and new values are added to previous ones. As the number of angles increases, the back projection improves. Now let's watch this video. So the first thing that's going to come up on this video is the acquisition, what represents the acquisition, okay? So I'm going to pause right here. So you're going to have, this represents the object that we're forming as we do the acquisition. This represents the projection that's being seen in energy, and then you'll see the sinogram get built over here, okay? So our object's going to be in the middle. Here's our camera head. Our camera head circles around. This is the energy it's seeing. As it circles, it's throwing those slice. Now remember, this is just one slice. So you're going to have a bunch of these for every part of the matrix. Boom. Okay, so it completed that, and it made a sinogram. So now here's all the data it needs to reconstruct that slice. So now we're going to watch the reconstruction as it throws it across the matrix multiple times. Okay, so I'll pause. So here you're going to have the object that's being reconstructed. It's going to show the original object and what it looks like. Our sinogram will be down here, so you'll see a line kind of follow through the sinogram as it puts it up on here in a reconstructed form. Okay, I'm going to pause right here. Okay, so there's our sinogram, energy levels that it's seeing, and the original image. So this is the first slice, or the first, the first projection. So the camera was, either below or up or wherever it was, and it threw that entire projection across the matrix. Okay, and so that's what you're seeing, is that whole thing just got thrown across the matrix. That's the intensity of gamma rays that it saw, and it threw it across. So now you're going to start seeing that as we move in the different positions of the camera head, more slices, more thrown across until it eventually forms the image. Okay. Boom. Now we call this filtered back projection because there's filters applied. There are filters applied. You'll notice that it gets a lot of junk out here in space, right? Because we've thrown it across the matrix. So what'll happen is you get this central image formed, and then there's filters that are applied that take out some of this stuff in the space. And we'll talk about some of those filters next and kind of how it works. But that's the main idea, is that as you cross it multiple times, you end up forming a projection. And you get, this happens for each slice along the image that you formed, okay? Watch this again, go back and look at it. This video was really helpful for me to kind of learn how this works, but that's filtered back projection. Filtered back projection is used here. It can be used in PET, it can be used in other modalities as well, but that's how it works. Okay, now iterative. Iterative is kind of convoluted, and basically what I want you to understand is that it's a mathematical process that your camera does. What it will do is it will look at it still looks at your data that you gathered. It looks at each projection. And then what it will do is it will guess based on how much activity it sees in the first projection. It will guess where it's supposed to be placed in the matrix. And then it will go back to the next projection and see if that projection lines up with its guess. And it will do that over and over again in what we call an iteration. So iteration just means it tries multiple things until it gets it right. Let me give you a brief explanation with this super simplified version. So these boxes, say, just represent four pixel elements, right? And so what you see here is coming through this way would be like your camera head's over here, and so you're getting energy that comes through here, and this is going to represent where radiation was from the patient, right? So this is how much activity is here. There's 5, and it's not millicurie. It's just a random number to represent. But you got 5 of activity here, 7, 6, and 2. And so the camera head, when it's over here, and it's just seeing what's coming off of the patient, it's seeing 12. It doesn't know where there's a 5 and where there's a 7. It just sees 12. Same thing here, 6 and 2. It sees 8 in intensity, but it doesn't know where they're at, and so on and so forth. So in this first slice, it gathers one set of projection data on the first projection coming through in one direction. And so then what it will do is it will say, okay, I know, for example, on this first one, it sees this 11 and it sees 9. And it knows it has 4 pixels to fill. So it says, well, I know I'm supposed to have an 11 and a 9, so I'm just going to split them in half because I don't know where they're supposed to go. So it'll put 5.5 in both of these, and it'll put 4.5 in both of these because 5.5 and 5.4 is 11, 4.5 and 4.5 is 9. So it does that guess. And then it goes back to the next projection, and it says, okay, let's see how that compares with my next set of data that's coming in. And what happened is when it looked at the next set of data, it looked at it and it went, well, I think that the data should say 10, but when I looked at the data, it actually said 12. I'm like, shoot, I as the computer got it wrong. Let me reassess. If it's supposed to be 12, then let me divide that up. And what it decides to do on the next one is it says, I'm going to do 6.5 and 5.5. And down here, I was supposed to be 8, and I guess 10. I was wrong there too, so I'll take 2 away. I'm going to do 4.5 and 3.5. Then it looks at the next projection, which in this case is going through at an angle. And it guessed by adding 4.5 and 5.5, I should have a 10. Well, it looks at the next projection and it's like, oh, I was wrong again. It should be a 13. So then it adds 3 and splits it up differently. And this time it puts a 6 and a 7. And then it does the angle going through this way and does the same thing. And eventually, when you do enough of these iterations, it gets to where it can accurately guess the math that is accurate with the original projection. Now, you might say to yourself, why in the world would you just want to guess when you have all the data and it's looking at the data? Why would you do this? The reason is that instead of having everything thrown across the matrix, so you get all this extra stuff out in space and you have to put a filter on and try to make the image look better, what this does is the computer can now say, okay, I know exactly where this intensity should be in my matrix, and so I'm only going to stick it there. And I don't even have to mess with back projection around all these other areas. I can just stick the intensity of gamma exactly where it needs to be. And so you tend to get a better image with less filtering needs. It's putting it exactly where it needs to go. Now, you can also imagine you have to have pretty good computer resources to do this. Because remember, if we go back a couple screens to our matrix, remember how many picture elements we have? Usually require a spectrum probably like a 128. So you're talking about 16,000 of those boxes. Okay, we're doing 4. So you use 16,000 and you have to do all the calculations through all of those boxes. You can see why it's kind of mind-blowing and a computer would have to do it. So high computer resources. So you can see why filter back projection was used initially, and as computers got better, you see a lot more iterative reconstruction now, to where it's a mathematical process and can put things on where they need to be. Okay. What I want you to know is you don't even know how to figure this out or look at the boxes and do math. Just understand that it's a mathematical process that looks at your projections, makes guesses, and then iterates and changes based on each projection what it should be until it gets it right, until it matches. Okay. I've listed here kind of the advantages and disadvantages of both, but with your iterative, if you do have artifacts that are in your image as you're going around, you tend to get less artifacts, less noise, less streaking. Again, disadvantage is that you need the computers, although nowadays they're highly available, so it's not even really a disadvantage. And then filter back projection, it's simple. There's not need for like the computers being so high tech. Disadvantages is you can get ring artifacts, noise, streaking. You imagine if there's one artifact somewhere in your image, it's going to represent that in every time it goes around, and you can get just a lot more noise and issues and problems. Okay. So let's talk about kind of some of the common filters that are used. You have the filter is going to either essentially sharpen an image or smooth an image. That's kind of your two types. So a high pass filter removes low frequencies and sharpens the image, and a low pass filter removes high frequencies and smooths the image. So what do I want you to take out of that? Remember that low frequencies are responsible for more of a smoothing effect, and high frequencies are responsible for more of a sharpening effect. Okay, so if we have a high pass filter, it's telling you what it's letting pass through. So a high pass filter sharpens, right? Because it's not letting the smooth frequencies through, it's letting through the high frequencies, which are sharpening. Opposite on a low pass filter, it's letting the low pass come through for smoothing effect, and it's cutting out the highs, okay? And so the common one that you should know is a ramp filter. Down here, you're looking at the frequencies, and here you're looking at how much filter is applied, okay? So again, low frequencies, remember, are smooth, and high frequencies are sharpness. So a ramp filter, again, you see that it cuts out low and lets through high, right? So again, a ramp filter is gonna get rid of blurring and sharpen an image, okay? And then the other two that I want you to know are a Hanning filter and a Butterworth filter, and these are more of your smoothing filters. So these are some views of a heart, and the original image is unfiltered, and then these other images are filtered degrees on both the Butterworth and the Hanning. So this is a low pass, meaning we let the lows through and we cut off the highs, so we get a smoothing effect, okay? And the difference with the Hanning and Butterworth is just that the Butterworth will keep more of the low end in before it cuts, okay? So it'll get some of those kind of mid ranges. But those are the two things. So know what a ramp filter is, know what a Hanning filter and a Butterworth filter is. Remember that the ramp filter is the high pass, Butterworth and Hanning are the low pass, and then just kind of generally understand how they're functioning. Okay, scintillation. Oh, QC. So this is the last thing we're going to go through, and then we'll be done. So hopefully within a couple of minutes, we didn't go too long. So the QCs for your camera that we're going to go over are uniformity, spatial resolution, COR. I listed peaking here. I want you to go read peaking. I'm not going to go over it. I don't think you'll see a lot of testing on it, and it's done by a physicist most of the time. But it just looks at the ability of the photomultiplier tubes to kind of stay even with one another. So that's about as much as I'll give you on that. Your license at your facility may require some additional tests besides these, and it may slightly alter the time intervals. What I'm going to give you is what's likely going to be on your boards, and we'll go over these sort of again when we do quality assurance in the summer, and do reminders, and you'll be doing stuff in your review class that will get these all written out for yourself and everything like that. So right now, just absorb it in. Each of these tests can be done on a gamma camera, what we call an intrinsic or extrinsic, okay? And that just depends on if your heads are on or off. So intrinsic is with the collimators. Intrinsic is with your collimators off, extrinsic is with your collimators on. So intrinsic would be more of a function of like looking at crystals and photomultiplier tube, and then extrinsic would be just like a general function of the camera as you would use it daily, okay? And then we'll talk about, you use some sheet sources of radiation, there's water sources, and there's also point sources that can be used. And some of those can vary depending on your camera and the manufacturer and things like that. So the first thing we're going to talk about is uniformity or uniformity floods. You guys, I'm sure, are used to doing these. You can do these intrinsic or extrinsic. Like I said, intrinsic would be with the collimator removed. You're going to have, for intrinsic, usually you have a point source that does the flood. So it's a little, usually you have some kind of device that hangs it out over the camera, and it's a little point source of radiation, usually like in the tip of a syringe, or some come where you can have actually a source that is like a sealed source. Usually you get counts between 10,000 and 40,000 counts per second. And again, it's placed away from the collimator. And usually you're going to require 30 million counts to determine uniformity accurately, okay? If if you 5 to 10 million counts are required to determine if it rises above an actionable limit. So let me say what I mean by that. When you guys do your daily floods, which are usually extrinsic, you usually do like a 5 million counts, right? And all you're doing with that daily one is you're trying to determine really quickly if the uniformity is out enough that you have to do something about it. That uniformity number is 5%. So when you get done with your daily floods and you're looking at the numbers that come up, those numbers should be below 5%. So usually you're seeing like 3.14 or 3.4 or whatever it might be, right? And that just means your uniformity is a quick check to see that your uniformity is where it should be. When we talk about doing these 30 million counts, what the camera is doing is it's actually looking at the every single crystal and every portion of the whole crystal and every photomultiplier tube, and it's looking at what they're gathering. It knows that your flood source is a uniform source. It's exactly the same across. That's the way they're manufactured, is to be same amount of counts across the entire thing. What it does is it takes that 30 million counts and it actually slightly makes slight adjustments in the photomultiplier tubes and wherever it needs to in the camera to make those things equal. So it's a way of the camera kind of setting itself up to be perfectly equal across all tubes, okay? So I want you to separate those two in your mind, that the 30 million is about getting uniformity. It's a quality control, but it's also something your camera does to set up and function accurately. And so that one's done on more of a monthly basis. And then your one that you do in the morning, your morning floods, is just to check for any abnormalities overnight that are obvious in uniformity that you'll be able to see or that go above that 5% mark, okay? So that's intrinsic. And then extrinsic is the one where you're going to have usually you have your sheet source. Those are usually good for about 2 to 3 years. But you're going to require it probably around 5 to 10 million counts, somewhere in that neighborhood. Every facility can be a little different, but it's somewhere between 5 and 10. And that image, you want to look at that image, you want to look at the numbers. Again, we want to be below 5%, and then we want to look at our image and see that it looks nice. And you've probably seen these at your facility. You should see a nice uniform image. If you find one spot that's too dark, that's darker or lighter than another, that could be a photomultiplier tube is not functioning correctly, and you may need to run your 30 million uniformities. And then if that doesn't work, then you probably have an issue with your cam, okay? That's your floods. The other one that we do for spatial resolution can be done intrinsic or extrinsic. And this is done with a 4-quadrant bar phantom. I always put caution on here because, again, that thing is heavy. It's full of lead septa. That bar phantom, in fact, here's a picture right there. So each of these dark spots are like the lead septa, and it's really heavy. If you're doing intrinsic, meaning your collimators are removed, and you drop that onto your camera, you're going to crack your entire crystal. Your camera's going to be down, and they're super expensive to replace. So you're probably going to get in some trouble. So if you're doing intrinsic bars, be very, very careful. Be very careful, okay? When you review these images, you should be able to see a resolvable difference between the very smallest bar pattern. Again, these are usually 3 to 5 million counts that are required. And again, extrinsic's just done with the collimators on. And here's your picture. So again, we're getting we can see a pretty good resolution. Notice it's not perfect. It's starting to get out of resolution, but again, I think I write it down. Yeah, right here. So that the low, no, I didn't write it. Those collimator, the holes are usually somewhere in the neighborhood of about 3, 4 to 5 millimeters. Like they get pretty small. And so that tests that like limit of your cameras. Remember, most gamma cameras have about a 3 to 4 millimeter resolution. So this is going to test like that fine resolution. So they aren't always perfectly looking, but you can see the differences. And so this is about what a bar phantom should look like. Spatial resolution is also tested for SPECT, and this is called a JSAC phantom. I think JSAC was like the inventor of this particular device. But essentially what happens here is this has a little cap that you can unscrew and you can put some technetium in here. So you'll put some technetium in there, and then you actually put this on your camera and you perform a SPECT. And then it's going to reconstruct slices of this image, and you should be able to make a distinction between the smallest spheres in these patterns. And so that's going to check your resolution on spec. Now, a resolution for a spec camera, I talk about this more specifically when we're comparing it to PET. But I said the resolution for a gamma camera doing just static images in flows is 3 to 4 millimeters. When we have to then reconstruct an image for SPECT, you go up closer to about 12 millimeters. So it gets a little worse. But that's just, again, with the reconstruction process, that's just the best you can do on SPECT. When we talk about PET, we get the images that are reconstructed down to about 3 millimeters again. So again, the reason why PET's a lot better in terms of resolution than a SPECT. Okay, last thing I'll look at is center of rotation. So this evaluates the alignment between what's happening mechanically as your camera turns around your patient, and being able to accurately represent in every single acquisition along that circular pattern where activity is represented in time and space when it does reconstructions. So this test is acquired by using a point source, and usually you have something you set on the end of your camera that has an arm that brings that point source into the middle of the camera, and then you spect around that, and your camera will have a software that shows you how many millimeters that spot stays within. And it's not supposed to shift more than 2 or 3 millimeters. When it does, it can significantly degrade the spatial resolution when the construction happens. Have your tech show you this. Usually they have a place on the camera control station, or you can watch and you can see usually a pattern of where that image is and how close to staying within that couple of millimeters it's doing. This is usually done every 1 to 4 weeks. Oh, and I don't think I mentioned on the uniformity floods, again, your 5 millions are daily, your 5 or 10 millions are daily, and then your 30 million is monthly. And then center of rotation, I've actually, in most facilities I've been in, they do this once a week. In the textbook, there are some that say monthly. So I would probably go with what the textbook says. But I think a lot of facilities do that on a weekly basis. So, all right, we made it, guys. Sorry, that was long. That was really long. Any kind of quick questions to wrap up, and I'll let you guys go.
I had one that had to do with kind of the uniformity. Not the uniformity flood. We do it once a month, and it's kind of like an open flood with a point source, but you see all the circles on the images. Are those the PMTs that we're seeing when we're doing that filling?
Yep.
Okay.
You get a picture of that. That's exactly right. So instead of looking like this, it would look like a bunch of circles with a little bit of dimness in between them, a bunch of kind of circular patterns. But yeah, that's what you'll see when you're doing a uniformity flood. Like I said, it's testing also the collimators and kind of when you're doing. Sorry, that's not what I meant to say. I meant to say when you're doing extrinsic flood with the collimators on, you're kind of representing system, and so they use this flood source because they just want to see that you can get a uniform picture out of your camera. When you're doing those intrinsic floods, it's more of a test of directly upon the crystal and each photomultiplier tube. So usually what the image that comes up is showing you each photomultiplier tube so that you can look at it individually and see that it's functioning the way it should. So good question.
And then I guess another one, since I have you here, what's the purpose of rotating the bars every week so you get a different like quarter on each
also
part?
A great question. The idea behind it, let me get back to that picture. The idea behind it is if you leave them the same way every time, then you could arguably make the case that, well, what if I have a certain area that is showing good resolution kind of going vertically, but maybe not horizontally here, and I'm only seeing horizontal here. So maybe I have a PM tube that's doing something weird over here. So a lot of techs will shift it each time they do it. They'll shift it slightly just to guarantee that we're not missing something in between those small areas. It probably wouldn't do that much, but that's the principle behind moving it. These are so small that your photomultiplier tube is quite large behind there. I suppose you could make the argument, though, that maybe you have an issue, maybe one of your boreholes and septa have a slight irregularity. I've seen with these bark phantoms, I've seen them dropped on collimator heads, and then you can get little bends in some of the boreholes, and that can cause problems too. So you could make that argument that possibly, boreholes go down to 3 millimeters. So the idea of turning that is just to make sure that you don't have the same areas of count showing and areas of blocking with the bars showing each time. So good question. All right, I'm gonna stop sharing. I would just say now. Oh yeah, go ahead. Yeah.
Oh, just saying thanks.
Oh, you're welcome. I had a question. Yeah, so I'm gonna stop sharing. I'll end the class. Again, get your test done for this new one. If you haven't done your other test, hurry and get that one done. Do your test corrections, and I will see you next time. I mean, we meet in October again, so next time we'll be going over again gas field detectors and some of the other ancillary equipment that we use. So, all right, I'm gonna let you guys go. See you later.